Why does light move so fast? And yet why can't it move any faster? Why is it that light, this radiant messenger from distant stars, always obeys a very specific rule, 29,992,4588 meters per second, no more, no less? Why does the universe care? And what happens if we try to break that rule? Because this isn't just a number. It's the thread that ties time, space, gravity, and matter together. It's the invisible ruler that measures reality itself. You may think this is a simple question, but it opens a door to black holes, to warped time, to the edges of the cosmos, and the limits of what we can ever know. Tonight, as you rest, let this be your journey, a quiet unraveling of the deepest mystery in the universe. Why does light have a speed limit? And what is it trying to tell us? Chapter 1. The speed that shapes everything. The universe is filled with motion. Planets spin, stars drift, galaxies spiral, like colossal pinwheels on a canvas too large for any one mind to fully grasp. But beneath all of this beautiful motion is something even more constant, something invisible, yet undeniable. It is not a thing we can touch. It is not a sound we can hear, but everything we see, everything we measure, and everything we know depends on it. The speed of light. For most of history, no one really considered that light had a speed at all. It just seemed to be there, instantly. You strike a match, and the light appears. You open your eyes, and the world is lit. But light is not instant. It travels, and it travels with a precision so absolute that it might just be the most sacred number in all of physics, 209,792,458 meters per second. Not approximately, not roughly, exactly, but why that number? Why not a million? Why not infinite? Why should there be a speed limit at all? To ask this is to begin walking a path that leads, not just to photons and physics formulas, but to the very edges of reality. Because this limit, this cosmic speed barrier, is not just a quirk of the universe. It is the structure of the universe. We call it C, the ultimate constant. It is not just how fast light travels. It is the maximum speed at which anything, energy, information, even cause and effect can move. It is the speed at which time slows, at which mass stretches, at which reality bends. And yet light itself is strange. It is not like a baseball, or a car, or a spaceship, that can speed up or slow down. Light does not accelerate. It does not need to. The moment a photon comes into existence, whether from a light bulb, the sun, or the collapse of a distant star, it moves at its full speed, instantly. No warm-up, no ramp, just go. But what is light? Is it a particle, a wave, a vibration in a mysterious field? Yes. And also more than that, light is a quantum object, a shimmering, dancing fluctuation in the fabric of space itself. It is born from change. A charged particle wiggles, and a photon emerges. But once it exists, it becomes something else entirely. It becomes the one thing in the universe that moves through time. Not at all. Yes, you heard that right. A photon, traveling at the speed of light, experiences no time. From its perspective, it leaves a star and arrives at your eye in the same instant. No waiting, no journey, just origin and destination collapsing into one. This alone should stop us in awe, because if light travels through time without aging, without delay, then what does that say about the nature of time itself? To begin to understand why light has a speed limit, we must also ask, what is it moving through? In our day-to-day world, speed is relative. A car moves through air, a boat cuts through water, even sound needs air to carry its waves. But light doesn't need anything. It moves through the vacuum, through pure nothingness, through the empty fabric of space. And yet, even in that pure void, it obeys the same speed limit. No faster, no deviation. It is as if the universe is built upon a kind of invisible grid, a structure that tells light exactly how fast to go, and nothing more. And it turns out, It is. That structure is spacetime, the four-dimensional stage, upon which all events, all objects, all motion takes place. And in that stage, light does not bend to our desires or expectations. It moves as the geometry allows. Albert Einstein saw this more clearly than anyone before. He realized that space and time are not separate things. They are not containers in which matter floats. They are interwoven, like threads in a cosmic tapestry, and the tension in those threads, the way they curve, stretch and shift, is what gives rise to gravity, inertia, and yes, the speed of light. The more you think about it, the stranger it becomes. If you could somehow ride alongside a photon, travel with it, match its speed, time would stop, distances would shrink to zero, everything would freeze into a single frame. But of course, no object with mass can ever do this. To reach the speed of light is to require infinite energy, and infinite energy is something the universe simply does not allow. But why? Why place such a boundary on motion? The answer lies not in light itself, but in the nature of information, of cause and effect, and of reality's need to remain consistent. If signals could travel faster than light, effects could precede causes, time could loop back on itself, logic would fracture, the universe would unravel into paradox. Light's limit then is not a constraint, it is a protection, a safeguard, a rule that prevents chaos from bleeding into order. And yet, despite this sacred limit, the universe plays tricks. Near black holes, light curves and slows. In quantum mechanics, entanglement seems to jump across space with no time delay. And in the early moments of the cosmos, space itself expanded faster than light could ever travel, stretching the young universe in all directions, far beyond what any photon could have reached. But even in these strange moments, the speed of light holds steady. It is not always about how fast things move. Sometimes it is about how the fabric moves beneath them. That's the paradox. That's the beauty. Light, which lets us see everything, is itself so simple, and yet so mysterious. It is the cosmic messenger that arrives without ever aging. The boundary between past and future. The clock that all other clocks obey. The rhythm by which reality dances. And the more we understand it, the more we understand ourselves. Not just as beings of matter, but as beings who exist in time, who move through space, who witness a universe bounded by law, but never lacking in wonder.
Chapter 2. What light is, and what it isn't. To understand why light cannot go any faster, we must first understand what light actually is. And the truth is, light defies the categories we try to place it in. It is not a particle in the ordinary sense, not a wave in the classical sense, not even a thing you can pin down to a single point in time or space. Light is an event, a transformation, a ripple in the very nature of the universe. Imagine shaking a rope. The wiggle travels down the line, even though no part of the rope flies forward. In much the same way, when an electron changes direction, it creates a disturbance, a ripple in the electromagnetic field that stretches across all of space. That ripple, traveling outward at exactly 299,792,458 meters per second, is a photon. Light is that ripple made real. But this is not like a stone skipping across a pond. The photon does not drag anything with it. It is not pushing particles through space like a sound wave through air. Light is pure energy. It is a self-sustaining electromagnetic wave. The electric field creates the magnetic field, and the magnetic field creates the electric one, in a perfect loop that feeds itself forward, traveling without friction or resistance. And yet, this elegant loop has a limit. This is where things get interesting. The speed of light isn't chosen randomly. It is baked into the very equations that describe electric and magnetic fields, known as Maxwell's equations. These equations, written in the 1800s by James Clerk Maxwell, describe how electric charges and currents create electric and magnetic fields. And when you solve them, you discover something stunning. Light must travel at a specific speed, and that speed falls out of the math naturally. It's not just a limit, it's a requirement. That value, c, depends on two fundamental constants: the permittivity of free space,
and the permeability of free space. These two strange properties define how electric and magnetic fields behave in a vacuum. They're like the stiffness and springiness of space itself. The tighter those fields push and pull, the faster the wave can propagate. But because those properties are fixed, determined by the very nature of the vacuum, the speed of light is fixed too. It's like asking how fast can a ripple move through a trampoline. The answer depends on the tension in the fabric. If the fabric is looser, the wave moves slowly. If it's tight, it moves quickly. But if that fabric is the vacuum of space itself, then that tension is not adjustable. It simply is. And so the ripple, the photon, moves at its set speed, always and forever. But this brings up a deeper question. If light is just a ripple, can it ever rest? No, it can't. Photons are what physicists call massless. They have no rest mass. They do not slow down, ever. In fact, they cannot slow down. They don't even have a valid state of existence at rest. You and I can sit still. A ball can lie on the ground. But light cannot be still. If you try to stop a photon, it ceases to exist. It vanishes. The moment it is born, it is in motion, and it remains in motion until it is absorbed. This tells us something fundamental. Light is not a thing in motion. It is motion itself. It is the expression of change, the breath between particles, the link between energy and information. And here's where it bends the mind even further. From our perspective, watching a photon leave the surface of the sun and travel for 8 minutes before entering our eyes, it seems like a long journey. But from the photon's own perspective, it experiences no time at all. The moment it is emitted, it is absorbed. There is no in-between. This is because time, in Einstein's theory of special relativity, depends on speed. The faster you move, the slower your internal clock ticks, compared to someone who is. And if you could somehow reach the speed of light, if you were a photon, your clock would stop completely. You would be frozen in time. Not slow, not delayed, frozen. Entire lifetimes could pass outside you, but you would not experience even a moment. This is not a metaphor. This is how the math works. A photon from the cosmic microwave background, created just 380,000 years after the Big Bang, has traveled for 13. It has seen the rise and fall of galaxies, the birth and death of stars, the emergence of planets, and yet, from its point of view, it has experienced none of it. It left and arrived in a single instant, as if space collapsed into a dot and time was erased. But how can something that moves like this, so fast, so strange, be a limit for everything else? Because that speed isn't just a property of light, it's a property of space-time. Einstein realized that the speed of light is the maximum speed at which any influence can travel. It's not about light itself, it's about causality, it's about preserving the order of things. If something could move faster, it could reach a place before a signal had time to get there. It could influence an outcome before its cause. It could break the sequence of time. And so the universe forbids it. This limit is not about friction or resistance. It's not about pushing against some invisible barrier. It's about the very shape of the universe, the way time and space are woven together. In this tapestry, the speed of light is the slope of the thread. It defines how fast information can move between 2 points. It defines what can be seen, what can be known, and what can be affected. It's not just speed, it's structure. That's why even gravity, the bending of space itself, cannot escape this limit. Gravitational waves ripple outward at the speed of light. Nothing, not even space-time's own trembling, can move faster. Still, there are strange exceptions, or so they seem. In quantum mechanics, entangled particles appear to affect each other instantly, no matter how far apart they are. In the early universe, inflation expanded space itself faster than light could travel, and in certain exotic materials, group velocities of light can seem to exceed. But none of these actually break the rule. In every case, information, the ability to send a message, cause an effect or change a state, never outruns light. The law holds, the limit remains. It is not about motion through space. It is about the boundary of what is physically meaningful. So when we ask why light has a speed limit, we are really asking, why does the universe need limits at all? And the answer may lie in the next ripple, the next wave, the next whisper from a photon that's been traveling longer than life itself. Chapter 3. Why you can never catch a photon. Imagine this. You're in the fastest spaceship ever built. An impossible craft that can accelerate forever without limit. You decide to chase a beam of light. You punch the engines. You go faster and faster and faster still. Yet no matter how much speed you add, that light beam always stays just ahead of you at the same unreachable distance. You never catch it. No matter how close you think you're getting, it always moves away at the exact same speed. 292,455 meters per second. You could pour infinite energy into your engines, stretch your ship across space and time, and still, that light beam would remain untouchable. But the real twist is this. The closer you get to that cosmic speed limit, the more the universe resists. It doesn't just push back, it transforms around you. Your ship grows heavier, time slows, distances stretch, space warps. Everything becomes harder, not because something is stopping you, but because you are approaching a fundamental edge of existence itself. And if you could somehow reach that edge, your mass would become infinite, your time would stop, and your ship would require energy the universe doesn't even contain. This is not a failure of engineering. This is the design of space-time itself. Einstein's theory of special relativity showed us that the speed of light isn't just about light, it's about the relationship between time, space, and energy. When you move faster, time slows down. When you move even faster, your mass increases. These effects are real, they've been measured, and at the speed of light, they become absolute. Now think about that light beam again. It's not accelerating, it doesn't struggle, it doesn't feel resistance. It simply moves, not through time as we understand it, but across it, as if time were frozen from its perspective. If you tried to reach its speed, you wouldn't just move faster, you would stop existing in the way you do now. Your idea of distance, of time, of self, would collapse. And this is why we say nothing with mass can reach the speed of light. Not because we haven't tried hard enough, but because to do so would require changing what you are. Light isn't playing by the same rules. It's not bound by time. It doesn't experience past or future. It exists in a strange state, where origin and destination happen all at once. And here's something even more astonishing. From a photon's point of view, there is no space between where it started and where it ends. It does not experience the journey. There is no path. It is emitted and absorbed. And to the photon, those events are the same. To us that's 8 minutes from the sun, or 2 million years from the Andromeda galaxy, or 13 billion years from the farthest galaxy we've ever seen. To the photon, it's instant. This shatters our usual sense of time. It breaks our intuition, and yet it is precisely what the math tells us. This is not poetic exaggeration. This is the structure of reality as best we can describe it. Let's take it one step further. Suppose you could somehow build a particle that could go faster than light, a so-called tachyon. What would happen? At first it sounds thrilling. Faster signals, time travel, shortcuts across space. But the math gives us a different answer. A particle moving faster than light would move backward in time. Its effects could precede its causes. You could destroy something before you created it. Messages could arrive before they were sent. And suddenly, the universe would no longer make sense. Events would lose their order. Logic would collapse. The simple chain of this leads to that would be broken. And if you break causality, the principle that the future should not influence the past, then every law of physics crumbles with it. That's why the universe doesn't allow anything to move faster than light. It's not a matter of speed. It's a matter of consistency. The speed of light is the limit that keeps reality stable. Even stranger, this limit applies not just to particles, but to information itself. If you want to send a message, a signal that carries meaning from one place to another, it cannot go faster than light. Not in air, not in a vacuum, not even through a wormhole or quantum tunnel. Every known law agrees. Nothing known to science can carry usable information faster than sound. That's not to say we haven't tried to cheat. There are materials where light seems to slow down dramatically, like glass, or water, or special crystal lattices. And there are tricks where wave groups called group velocities appear to outrun light speed, but every time, the signal, the information stays within the limit. No violation ever holds up to scrutiny. In fact, even the light we see is already slowing down in many ways. When light travels through glass, it bounces between atoms, scattering, pausing, delaying. But this is not breaking the law. The true speed of light in a vacuum remains untouched. The universe is strict about this number. It does not compromise, and that's what makes it so important. It's more than just a number. It's more than just a rule. The speed of light is the foundation of how things relate to each other. It tells clocks how to tick. It tells rulers how to measure. It tells forces how far and how fast they can reach. It is, quite literally, the backbone of reality. So when you look up at the stars and see light that's taken millions or billions of years to reach your eyes, you're not just seeing a point of brightness. You are witnessing the final moment of a journey that began before humans existed. A photon, born in fire, crossing the void, undeterred by time, untouched by age, obeying a rule that nothing has ever broken. And no matter how fast you move, no matter how far you go, you will never catch it. Not because it's running away, but because it's not moving through time, it's moving across it.
Chapter 4. Light and the Shape of Time. To understand why the speed of light matters so deeply, not just to physics, but to you right now, as you breathe, as your heart beats, as your thoughts drift, we must leave behind our everyday notions of time and space, because in the presence of light, these things are not what they seem. You are likely taught to think of time as a straight line, flowing forward, steadily, like a river, 1 second, then another, 1 moment, then the next. But this is only part of the story. Time is not separate from space. It never was. They are two sides of the same fabric, one seamless continuum called space-time. And light is the thread that binds that fabric together. It acts as the measure, the boundary, and the ultimate reference. Without light's fixed speed, there would be no way to say how fast time flows, or how long space stretches. The tick of every clock, the distance between any 2 points, all of it depends on light's unwavering rhythm. This is not just philosophy, it is mathematical fact. Imagine 2 events happening in different places, one on Earth, one on Mars. When exactly did each event occur? The answer depends on how fast you're moving. To one observer, the event on Earth happened first. To another, equally valid observer, moving in a different direction, the event on Mars came first. This isn't a trick, it's how space-time works. But there's one thing that all observers agree on: the speed of light. No matter how fast you're moving, no matter where you are, when you measure the speed of a light beam, it will always be the same. It never changes. And that's where the weirdness begins. To preserve this constant speed, time itself must adjust, distances must contract, simultaneity must break down. This is the heart of Einstein's special relativity, not just that time slows down when you move fast, but that time is not absolute. There is no universal clock ticking in the background. Time depends on the observer, and light is the enforcer of that dependency. Think of it like a cosmic referee. Every observer, no matter how fast they move or where they stand, gets the same call. The speed of light is always set. But to keep that call fair, the game itself bends. Space bends. Time bends. Reality reshapes itself to preserve that constant. This leads to some incredible consequences. If you're traveling close to the speed of light, you age more slowly than someone who stays at rest. This is not science fiction. It has been measured in astronauts, in particles, in atomic clocks flown on airplanes. Time dilation is real. If you watch a spaceship zooming past at near light speed, it appears shortened in the direction of motion, physically contracted, compressed by its speed. This is known as length contraction, and it's another real measurable effect of maintaining the speed of light's supremacy. And then there's the most stunning fact of all. Light doesn't just shape time, it defines causality, the very rule that says an effect cannot come before its cause. To preserve this rule, the universe draws invisible boundaries, light cones around every event. Anything inside the cone is reachable by a light beam from that event. Anything outside is not. That means you can only be influenced by,
or influence events within your light cone. Outside of that, it's too far, too fast, too. You are surrounded right now by a field of causality, a soft sphere expanding outward at the speed of light. Everything you could possibly touch, change, or affect in the future lies within that boundary. Everything that could affect you is racing toward you at the same speed. And that limit, the edge of influence, is set by light. It's an elegant design, no faster, no slower, just right. And that limit keeps everything in order. But what about the places where time seems to behave differently? Near a black hole, for instance, gravity is so strong that it bends space-time to the extreme. A clock placed near the event horizon ticks slower, far slower, than one far away. From the outside it looks like time is nearly frozen, but from the point of view of the clock itself, everything seems normal. This phenomenon is called gravitational time dilation, and again, light plays a central role. You see, light must climb out of that gravity well, and as it does, it stretches, its wavelength gets longer, its energy drops. This stretching is a sign, not just of gravitational pull, but of time itself being warped. Once again, light is not merely affected by space-time, it reveals its shape. By watching how light bends, stretches, or slows, we learn how time is behaving in places we can never visit. The deeper lesson is this: light does not just exist in space-time, it draws its boundaries, it sets its clock, it defines its map, and because of that, light's speed must be constant, not just for convenience, but because any deviation would cause the entire structure of reality to fall apart. Without a fixed speed of light, time could not be defined consistently, events could be reversed, clocks would not agree, causality would be lost. And this is why, despite all our curiosity, despite all our creativity, the universe remains immovable on this one point. Light's speed is not negotiable, it is not adjustable, it is a law, deeper than any written in ink, more permanent than any star. You can bend time, you can stretch space, but you cannot outrun a photon, because in doing so you would be trying to leave behind the structure that makes the universe make sense. And no matter how far you reach, you will always remain bound to the speed that binds time to space, and space to you.
Chapter 5. Light, Information, and the Edge of What Can Be Known. Light is more than just a glowing beam that travels through space. It's more than the warmth of the sun, more than the colors we see, more than the shimmer of water, or the glow of a distant star. Light, in the language of physics, is information, a messenger that tells us something happened, somewhere, sometime. And the moment you accept this, the speed of light becomes not just a rule for motion, but a rule for knowing. Let's begin with the idea of seeing itself. Every time you open your eyes, what you're really doing is catching photons, tiny packets of light that have traveled across time and space to reach you. A tree isn't seen in the present moment. You see it as it was nanoseconds ago, the time it took for light to bounce from it into your eye. The moon, that's 1.5 seconds in the past. The sun, 8 minutes. The nearest star, over 4 years. And the farthest galaxies we can detect, we see them as they were more than 13 billion years ago. We never see things as they are, only as they were, when the light began its journey. This is not some metaphorical poetry, this is literal truth. The further away something is, the further back in time we must look to find it. And the thing that separates now from then is the speed of light. It becomes a cosmic boundary, not just on motion, but on awareness. You can only know about an event once its light has reached you. If something happens in a galaxy 10 million light-years away, you must wait 10 million years for that light to arrive. Until it does, it is beyond your reach, not just physically, but conceptually. The universe has placed a delay on knowledge itself. Now consider this: if light had no limit, if it could travel instantaneously, then there would be no such thing as distance or delay, or isolation. Every event could be observed instantly, by anyone, anywhere. The universe would be flat, shallow, exposed. There would be no mystery, no unfolding, no anticipation. But with a finite speed of light, we are given depth, we are given past and future, we are given perspective. The speed of light is not just a wall, it is also a gift. It defines a horizon, a limit beyond which you cannot yet see. And because of this horizon,
We experience the passage of time. We witness the unfolding of stories. We live in a universe with a visible past and an invisible future, and light is what brings those two realms together. But it's not just about sight, it's about communication. The moment you speak into a phone, send a signal to a satellite, receive data from a probe drifting through the void, you are interacting with the universe through light-speed signals. Every message, every bit of information, is constrained by the same universal law. Even the fastest computer, the most efficient quantum system, the most advanced probe we could ever launch, none of it can send or receive faster than light. And that limit defines not just what is possible, but what is knowable. You cannot learn about something until its information has had time to travel to you. And here's where it gets even more profound. Light is not just how we receive information, it's also how the universe enforces cause and effect. If you flick a switch and a light turns on across the room, photons carry the news. If a supernova explodes in a distant galaxy, it's the light that tells us. But more than that, it's the light that keeps the order of things intact. You cannot affect something faster than a photon can reach. The rules of sequence, of causality, of first this then that, are all tied to this limit. Now imagine a universe without it. In a world where information could travel instantly, chaos would reign. Effects might precede causes. Messages could arrive before they were sent. Paradoxes would flood reality. You could destroy something before it existed. You could answer a question before it was asked. The linear arrow of time, the thing that lets stories make sense, would shatter. But our universe does not allow that. The speed of light is what holds the arrow steady. Even in quantum physics, that bizarre world where particles pop into existence, entangle and disappear, the rule still holds. Entangled particles may seem to communicate instantly, but they don't actually transfer usable information faster than light. The illusion of instantaneous action never violates the deeper law. Causality stays intact. This means light speed is not a constraint placed on photons alone. It is a constraint placed on the fabric of knowledge. It defines the speed at which truth can move through the universe. And when you zoom out, far out, into the cosmic scale, this becomes even more mysterious. The universe is expanding. Galaxies are rushing away from each other, carried by the stretching of space itself, and some of them are already moving away from us, faster than the speed of light. Not because they are breaking the rule, but because space itself is expanding beneath them. Their light will never reach us. They have passed beyond our cosmic event horizon, a boundary beyond which no signal can ever cross. There are parts of the universe we can never observe, never contact, never affect, not because they're too far, but because the light from them will never arrive. These regions are not hidden by dust or blocked by matter, or cloaked in mystery. They are simply unreachable. Light will never bridge the gap, and so in a very real sense, they might as well not exist, at least not to us. Once again, the speed of light defines the edge of what can be known, and perhaps this is the deeper beauty of it all. The limit is not there to frustrate us, it is there to shape us, to give the universe its rhythm, to create beginnings and endings, arrivals and departures, to let stories unfold over time, rather than all at once, to create moments, distinct, fleeting, real. Without it, the universe would be static, timeless, unchanging, but with it, we get sunrise and sunset, the flicker of stars, the echo of distant galaxies, the slow unfolding of time itself. We get discovery, we get mystery, we get the chance to wonder. And so the next time you look at the stars, remember, what you are seeing is not the present, but the past, a memory carried on the backs of photons, each one traveling faithfully across space and time, to bring you a tiny glimpse of what. You can never catch them, you can never outpace them, but you can always receive them, and through them, glimpse the rhythm of a universe built not for speed, but for understanding. Chapter 6. The stillness of a photon. Close your eyes for a moment, not just to rest, but to imagine something no one has ever truly experienced. The life of a photon, not its creation, not its destination, just its existence. But that's the paradox, because from the moment a photon is born, in the furnace of a star, the flick of a spark, the radioactive decay of an atom, it begins to travel at the speed of light, instantly, without delay, without acceleration. And from that moment, until the instant it is absorbed, it experiences nothing, no time, no waiting, no motion, in its own frame, just a strange eternal stillness. To us, it travels billions of kilometers. To itself it never moves at all. This is perhaps the most unintuitive truth of all, that the fastest thing in the universe to its own perspective never experiences motion. It has no sense of distance. It has no awareness of time. In the strange geometry of space-time, the path of a photon is called a null path, a journey with zero interval. The photon is both here and there, both emitted and absorbed, in the same instant of its own timeline, which is no timeline at all. And this raises an almost mystical question. What is a journey that feels like no journey? What is a life that experiences no time? Is it even meaningful to say that a photon exists in the same way that we do? We, as creatures made of matter, are bound by clocks. We move forward, we change, we age. Every breath marks a passage. Every heartbeat is a beat in time. But light does not live this way. Light is the beat. It sets the rhythm. It defines the speed at which events can connect, and yet it dances outside of the tempo it enforces. This strange condition, to exist, but never experience, gives light an almost ghost-like quality. It reveals, it illuminates, it delivers, but it never reflects on itself. You might ask, how can something that doesn't age still have meaning? And the answer is simple, because it carries meaning to us. A photon doesn't see, but it lets us see. It doesn't think, but it reveals what is there. It doesn't experience time, but it defines the time between events. It is the silent witness, the silent messenger, the link between one moment and another. And its stillness, that unaging, undelayed stillness, is the reason why we can have a sequence at all. Think about this. The very notion that something can happen before something else only makes sense if we have a consistent way to connect the dots. Light provides that connection. It's not just a beam, it's a measure. It's the yardstick by which we draw time itself. And yet, despite its constancy, light can still be bent, not slowed, not aged, but redirected. It responds to the shape of space. It bends around stars. It curves through gravity. It stretches as space expands. Light obeys the contours of the universe, tracing invisible lines that show us where space has been stretched or squeezed by mass. This bending, called gravitational lensing, is not just a curiosity, it's a window. We have seen galaxies behind other galaxies, distorted into arcs and rings by light's path, through warped space. We have mapped the distribution of dark matter, not by touching it, but by watching how light curves around it. Light cannot lie, it cannot conceal. It follows the laws of geometry with perfect honesty. It is not slowed by gravity, but it is redirected by it, not because of force but because of shape. This tells us something profound. Space is not a background. It is not an empty void. It is a structure, a medium, a field with tension and flow, and light in its stillness travels not through space, but along the structure of space itself. And that structure is dynamic. When you shine a flashlight in the vacuum of space, you might think the beam shoots forward in a straight line, but it doesn't. It follows the shape of the universe, which is never perfectly flat. Space curves, expands, wobbles, and light adapts. It always moves forward, always at the same speed, but its path is flexible, like a dancer tracing the curves of an unseen rhythm. And in this dance, it reveals what we could never otherwise perceive. A photon arriving in your telescope may have traveled through dense gravity wells, over ancient cosmic mountains and valleys of space-time, twisted and turned by the invisible hands of mass and motion. And yet it arrives, exactly on time, not late, not early, just precisely when the universe allows. Now think again about the stillness of that photon, a stillness not in distance, but in experience. From its own point of view, its entire life is one instant, and from our point of view, it may be a journey of 13 billion years, and yet both are true. This is the great duality of light, timeless to itself, yet the very tick of time for us. We build our calendars, our technologies, our satellites, our definitions of distance, all from the constant sacred rhythm of light's travel. The meter itself is now defined by how far light travels in a fraction of a second. Our measurements are not just inspired by light, they are built from it. Every GPS signal, every scientific measurement, every telescope observation, they all depend on the certainty of light's behavior, and in that certainty, we find not just mathematical truth, but existential truth, a trust in the structure of reality itself. So while a photon may never feel the passage of time, it gives us the ability to measure it. While it never grows old, it brings us knowledge of what once was. While it never takes a single step, it bridges the distance between stars, galaxies and minds. The stillness of a photon is not a flaw, it is not a limitation, it is the foundation of everything that moves, changes and becomes.
Chapter 7. How mass stops you from reaching the speed of light. You've probably heard the phrase before, nothing with mass can reach the speed of light. It's repeated in classrooms, whispered in documentaries, written in textbooks. But why? What is it about mass that makes light speed forever out of reach? Why do we, and everything we know, have to play by different rules than photons? The answer lies in a quiet, invisible tension, a resistance that begins not in the air, not in friction, but in the very fabric of space-time itself. To understand it, we need to start simple. When you push something, a ball, a car, a rocket, it speeds up. Apply a little force, it moves faster. Keep applying force, and it continues to accelerate. In our everyday world, this feels limitless. But in the relativistic world, the world governed by Einstein's equations, acceleration is not so simple. Because the faster something moves, the harder it is to make it move faster. That resistance is not caused by mechanics or engineering. It is caused by energy, or rather the exchange rate between energy and motion. As your speed increases, so does your relativistic mass, a way of saying that it takes more and more energy to gain less and less additional speed. Approaching the speed of light, the energy required rises toward infinity. That's not poetic exaggeration, it's what the equations actually say. To push a spaceship to the speed of light would require an infinite amount of energy, and the universe, no matter how generous, does not deal in infinities. Now contrast this with a photon, a particle with no rest mass. It does not accelerate, it does not build up speed. The moment it exists, it travels at light speed. Why? Because there's nothing in it that resists. No mass to push, no inertia to overcome. It's born moving, and it cannot stop. It does not have the option to slow down. So mass, in a strange way, is a kind of anchor to time and space. It gives things substance. It gives them history. It makes it possible to be here now, and not there later. But that same gift, the gift of presence, is also a boundary. With mass comes resistance. With mass comes limitation. With mass comes a future that unfolds step by step, moment by moment, never all at once. And the closer you try to push mass to light speed, the more the universe resists. Not by friction, not by wind, but by demanding more and more energy for each microscopic gain, until finally, the cost becomes unreachable. Let's look at this visually. Imagine a graph where speed increases along one axis, and energy climbs up the other. For low speeds, the energy curve is gentle, manageable. But as you near light speed, the curve tilts upward, not in a straight line, but in a steep vertical wall, just shy of light speed. The curve becomes nearly infinite, and no amount of fuel, no amount of technology, can break through that wall. This is not a technological problem, it's a geometric one. Space-time is shaped in a way that makes the speed of light a horizon, visible, measurable, but never touchable. Even our most powerful particles, fired at unimaginable speeds in particle accelerators, never reach. They get close, within fractions of a percent, but always fall short. The faster they go, the heavier they get. The heavier they get,
the more energy is required to accelerate them further. And even at trillions of electron volts, nature says, not quite. But why does mass behave this way? Because of something deep, something subtle, something called symmetry. In physics, the laws of motion arise from symmetries, the idea that certain things remain unchanged when you shift your perspective. Conservation of energy, for example, comes from the fact that the laws of physics don't change over time. Conservation of momentum comes from the symmetry of space, and the speed of light. That comes from the symmetry between space and time themselves. Einstein's special relativity shows that when you transform between one observer and another, say someone standing still versus someone moving very fast, the only way for the laws of physics to remain the same is if the speed of light stays constant. And to protect that constancy, everything else must bend. Time, distance, mass, energy. So in a way, mass is a kind of tribute the universe collects, a way of enforcing balance. The more speed you want, the more energy you must pay. And the price gets higher, the closer you reach the cosmic ceiling. But photons never pay that tax. They're exempt, not because they're rebellious, but because they belong to a different category altogether. Massless, unanchored, timeless. Yet even massless things are not entirely free. Photons can be bent by gravity. They can be scattered by particles. They can be absorbed, re-emitted, polarized, delayed, redshifted, or trapped. They are not indestructible, but they are unwavering in one thing. So when you ask why you, or any object with mass, can't reach that speed, the answer is simply this. Because mass means memory. Mass means experience. Mass means you exist in time, and time, by its nature, cannot vanish. To reach the speed of light would be to exit time, to let go of sequence, to abandon experience, to become unanchored from the chain of cause and effect. And mass refuses to let that happen. Even at your fastest, you are still inside time, still unfolding, still bound to the flow, still grounded in the rhythm that light defines, but can never be part of in the same way. So next time you think about rockets and starships, warp drives and light sails, remember, it's not just about speed, it's about the deep structure of what it means to have a body, to have mass, to be part of a universe that unfolds, one moment at a time. You're not slow, you're just real, you're just present, you're just here. And the very fact that you can move through time at all means that you can never quite become light, and that in its own way might be more miraculous than speed. Chapter 8. How light travels through nothing at all. Light, unlike sound or water waves or drifting leaves on a breeze, doesn't need anything to move through. It doesn't require air. It doesn't need a wire. It doesn't need matter at all. It sails across the vacuum of space, complete, perfect emptiness, as effortlessly as it travels through glass, or fog, or flesh. But how can something move through nothing? This question confused scientists for centuries. After all, everything we knew about motion required a medium, a substance to carry the wave. Sound needs air, water waves need water. Vibrations need strings, solids, tension. So when it became clear that light could cross a vacuum, people tried to imagine what invisible medium it might be moving through. They called it the ether, an invisible substance that filled all space, perfectly transparent, utterly undetectable, yet essential for light to ripple through. The idea persisted for decades. It was elegant, it felt necessary, but it was wrong, because in the late 19th century, experimenters like Michelson and Morley built ingenious tools to detect the Earth's motion through this supposed ether, and they found nothing. No shift, no drag, no evidence at all. The ether didn't exist. And then came Einstein. With special relativity, he swept away the need for a medium. He showed that light doesn't require a background to move through. Instead, light is a ripple in the very fabric of space and time, not in a substance, but in the fields that pervade reality itself, specifically the electromagnetic field. Everywhere in the universe,
Even in what we call empty space, this field exists. It doesn't have weight, it doesn't shimmer, but it can vibrate. And when it does, when it oscillates in just the right way, it produces light. That's what a photon is, a disturbance in the electromagnetic field, a packet of energy born from the interaction of electric and magnetic components dancing together. The electric field wiggles, producing a magnetic field. The magnetic field wiggles, producing an electric field. Back and forth, each feeding the other, creating a self-sustaining wave that flies forward through the vacuum. So yes, light moves through nothing, but space is never truly nothing. Even a perfect vacuum, with all matter removed, still contains structure. It has energy, it has quantum fluctuations, it has geometry, and it has these background fields that make light possible. Now think about what that means. The emptiest space you can imagine between galaxies, between stars, even between atoms, is still capable of producing and carrying light. It still obeys the rules of electromagnetism, and it still provides the same sacred speed. This means that light's speed is not determined by obstacles or friction or resistance. It is determined by the properties of space itself, the stiffness of the electric and magnetic fields in the vacuum. These values, permittivity and permeability, are constants of nature, unchanging, precise, fundamental. They define how much an electric field resists being changed, and how much a magnetic field can grow in response. And together, they give rise to the speed of light, not as an arbitrary limit, not as a number chosen from a hat, but as the result of deep structural features of the universe. Now pause and consider how strange this really is. We think of empty space as absence, a void, a gap between things. But light sees it differently. To light, space is a highway, not one it crosses, but one it emerges from. It is not traveling on the field, it is the field, a local ripple, a tiny twist in the background geometry that moves always at the same rate, always forward, never slowing, never resting. And this is why light travels at the same speed no matter where it is. In a vacuum, in deep space, in the lab, in your eye, it moves at c, because the field is everywhere, because space is never truly blank. But introduce matter, and the story becomes more interesting. In materials like water, glass or diamond, light appears to slow down. This doesn't violate the rule. It's not that photons are literally changing speed. Instead, they are interacting. They are being absorbed and re-emitted, scattered and delayed, trapped for tiny intervals in atoms before resuming their path. The net result is a slowdown, but the photon between interruptions always moves at c. Always. This distinction matters because it shows that the speed of light, true unaltered light, is not something you can cheat. You can't make it go faster. You can only change the environment around it. You can stretch the path. You can lengthen the journey, but the pulse of pure light in a vacuum remains untouched. And this constant speed across all of reality does something miraculous. It creates the light horizon, the boundary between what can and cannot influence each other. No event can touch another unless there's time for light to connect them. No message can arrive unless there's a path, a bridge, a photon to make the trip. It's not about speed anymore. It's about connection. And the fact that this connection works across empty space, across nothing, means that the universe is wired for relationship, not isolation. Even in the darkest corners of the cosmos, where no planets orbit, where no stars shine, where space itself stretches silently into the abyss, a photon can still fly. It doesn't fall, it doesn't tire, it doesn't need to be carried, because the very vacuum, the nothing, holds the rules that guide it. That's the paradox. Light moves through nothing, because nothing, as it turns out, is something after all.
Chapter 9. What it means that light has no mass. Let us return to one of the simplest facts in physics. Light has no mass. You've probably heard it before, maybe even accepted it without much thought. But to really sit with that idea, to let it unfold fully, is to encounter one of the most profound and puzzling truths in all of nature. Light is massless. It weighs nothing. You cannot put it on a scale.
You cannot trap it in a box and measure its inertia. It does not resist acceleration, because it does not accelerate. It has no rest frame, because it cannot rest. And because of this, it lives at the one speed no object with mass can ever reach, the speed of light. But what does it mean really for something to have no mass? We are so used to associating mass with reality. Things feel real when we can touch them, lift them, weigh them. Mass gives things substance. A chair, a planet, a person. Mass gives them weight, presence, resistance. But light is different. It is both real and unreal, present and elusive, seen and ungraspable. When physicists say a particle is massless, they mean it has zero rest mass. That is, there is no possible way to observe it at rest. You can never sit with a photon. You can never catch it and ask what it's like to be still. It doesn't have that option. Its very identity is defined by constant motion, and that motion is always at sea, not as a coincidence, but as a necessity. If light were to go slower, if it had any rest mass at all, its behavior would change completely. It would age, it would experience time, it would require infinite energy to go faster and faster. But because it has no mass, it doesn't follow those rules. It moves at the speed limit of the universe, not because it's pushing hard to get there, but because that's the only speed it can have. In this sense, being massless is not just a property, it's a destiny. Now here's something else to consider. We often think of energy and mass as separate. Mass is what something is, energy is what it has. But Einstein taught us otherwise. In his most famous equation, mass and energy are two sides of the same coin. A stationary object, sitting still, has energy simply because it has mass. And conversely, even something with zero mass, like a photon, can carry energy by virtue of its motion. This is why light can warm your skin, why it can power solar panels, why it can damage cells, trigger chemical reactions, and push against the sails of a solar-powered spacecraft. It has no mass, and yet it does work. It has momentum, it has energy, it can exert force. But it exerts that force not through bulk or weight, but through pure motion, the relentless streaming of quantum packets, through the electromagnetic field. Even stranger, that energy depends on one thing: frequency. The higher the frequency of light, the more energy each photon carries. Red light has less energy than blue. Microwave photons are weaker than X-ray. And at the far end of the spectrum, you reach gamma rays, photons, so energetic that they can punch through atoms, mutate DNA, ignite reactions deep within a star. All of this from particles with no mass at all. It is a reminder that mass is not the only path to power. That motion itself, pure, constant, unending motion, can reshape matter, transfer heat, generate electricity, build the structures of life, and destroy them. And yet, this motion is timeless. From the photon's point of view, it is never moved. It is simply being a blur, across space and time, present only in relation to others. No clock ticks for it. No moments pass. We see it travel. We see it age. But it never sees itself change. In this way, photons exist like messages, pure bits of information moving from one point to another, never pausing, never lingering, never reflecting. And what are they carrying? Not just brightness, not just color. They carry structure. They carry the shape of the thing that emitted them, the direction, the energy, the pattern, the spectrum. They carry the fingerprint of distant stars, the whisper of chemical bonds, the echo of ancient explosions. And when they arrive, when they strike a surface, or an eye or a sensor, they vanish. A photon is not stored, it is not parked, it is either in transit, or it is absorbed. The moment you know it, you destroy it. The act of measuring is also the act of erasing. And yet, in that final moment, it gives you something. It gives you knowledge. Now imagine this happening billions upon billions of times, across space, across time. Photons leaving stars, bouncing off leaves, hitting mirrors, feeding telescopes, bathing the surface of planets, always moving, never resting, always arriving with no mass,
no weight, but with the power to reveal what would otherwise be invisible. Without mass, light is not burden. It does not lag behind. It does not fall. It does not decay. It just goes. And in doing so it defines the arena in which mass can exist. Because without light, there is no way to measure motion, no way to define before and after, no path, no speed, no time. The irony is clear. The thing with no mass becomes the thing that shapes the very experience of mass. The ghost defines the castle. The ripple defines the ocean. The massless defines the meaning. So next time you think of mass as the mark of reality, remember this: the light that reaches your eye, that paints your world in shapes and colors and depth, that lets you see yourself reflected in the mirror, that shows you the sky, the stars, the pages of your book, has no mass at all. And yet, without it, you would see nothing. Without it, you would know nothing. Without it, the universe would remain silent and dark and still. The massless makes the massive knowable, and the speed it moves, the one true speed, remains untouched, unchanged, absolute. Chapter 10: The Cosmic Clock That Never Ticks. Imagine, for a moment, that the universe is a vast machine, a quiet, unfolding mechanism with no visible gears, no ticking hands, no audible rhythm, and yet, something keeps time. Something tells the universe how fast to change, how far to stretch, how long to wait between events. That something is light. It may not tick, it may not chime, but light is the cosmic clock, not because it ages, but because it defines what it means for something else to age. In a world where light is constant, all other measures of time become relative. A second is only a second, because light travels a certain distance in that time. Our most precise atomic clocks, those that define the international standard of time, use photons emitted by atoms in transition. The rhythm of those emissions, that steady flickering pulse of light, becomes the heartbeat of time itself. We often forget how much we depend on this. Every GPS satellite, every network signal, every timestamp, every deep space communication, all of them depend on the unchanging rhythm of light. The constancy of its speed is not just a scientific curiosity, it is the bedrock of our ability to agree on anything at all. But let's go deeper. What does it actually mean that the speed of light is the same for everyone, everywhere, no matter how fast they're moving? It means that time, the thing we think of as absolute, is actually something malleable, flexible, adjustable, but only in such a way that the speed of light remains sacred. Imagine two people in two different spaceships, each moving at vastly different speeds. They shine flashlights, they check their watches, they compare notes, and even though their clocks run at different rates, even though their distances stretch or shrink depending on their motion, both of them always measure the speed of light to be exactly the same, and that consistency forces everything else to adapt. To preserve this constancy, time itself slows down for the fast-moving traveler, not subjectively, not perceptually, act. And if one of those travelers were to return after a long, fast journey, they would find that more time had passed for those who stayed behind. This is not a trick of perspective. It is real. It has been measured. Muons created in Earth's upper atmosphere live longer than expected because they are moving close to the speed of light. Their internal clocks tick more slowly. Astronauts orbiting Earth experience slightly less time than people on the surface. And one day, when we send humans on deep space voyages, they may return younger than their siblings left behind. But again, light never changes. The photons exchanged between the travelers, the signals received, the images seen, always follow the same rule, always move at the same speed, always obey the cosmic constant. This is why physicists refer to c, not just as the speed of light, but as the fundamental unit of causal structure, the speed at which information, influence, and existence itself can ripple through the universe. If it were variable, if it could change from place to place, or observer to observer, then the rules of causality would break down. Some events would happen before their causes. Some messages would arrive before they were sent. Reality would dissolve into contradiction. But that never happens, because light, massless, Ageless, relentless light never varies. It is the needle in the compass, the line in the sand, the one thing that stays put while all else flows around it. Even black holes, those most extreme distortions of space and time, must bow to this rule. Light fired from near the event horizon stretches and bends and slows, as seen from far away, but its local speed never falters. Even as time nearly stops at the edge of the abyss, the photon still clings to its speed, racing outward along a path that becomes longer and longer as space itself stretches. That is the paradox. It defines motion for us, and yet it never accelerates, never rests. It defines distance for us, and yet from its own perspective, the space between departure and arrival is zero. This contradiction is not a flaw. It is the blueprint, the structure, the paradox at the heart of how we move, how we age, how we relate to anything beyond ourselves. And so light becomes more than a thing. It becomes a principle, a foundation, the scaffolding on which time itself is built. When you check the time on your phone, you are not just reading a number, you are witnessing a series of synchronized pulses, each one defined by electromagnetic waves. When a telescope captures a signal from a distant galaxy, it does not just collect light, it collects the history of time in motion. In this sense, light is not just what allows us to see the universe, it is what allows the universe to unfold. It is the rhythm of the cosmos, and the fact that it has a limit, a fixed, unchangeable speed is not a hindrance. It is the harmony. Without it, the orchestra of time would fall out of sync. Without it, the stories of stars and atoms and people would have no coherence, no causality, no direction. So the next time you hear that light is fast, remember, that's not the point. Light is not fast. It is final. It is not a blur. It is the boundary. It is not racing through time. It holds time together. And as the universe expands, as stars are born and die, as matter clumps into galaxies and collapses into voids, light continues to ripple, not to chase, not to escape, but to measure, to define, to hold everything in motion, together.
Chapter 11. Can anything go faster than light? The speed of light is more than just a number. It's a foundation, a universal constant that underpins every law of motion, time, and causality. Nothing, according to the known rules of physics, can travel faster. It's a boundary the universe itself seems to protect, not with walls or barriers, but with consequences. And yet, one question still lingers in the minds of scientists, thinkers, and storytellers alike. Could anything, in any corner of physics, possibly move faster than light? If such a thing existed, it would change everything. Distances would lose their meaning. The vast spaces between stars would become accessible. Messages could cross the cosmos instantly. Time might bend, or even reverse. The entire structure of reality, causality, simultaneity, history, could become negotiable. But to seriously consider such a possibility, we must understand what the speed of light really limits. It doesn't simply restrict how fast objects can move. It defines the maximum speed at which information, and therefore cause and effect, can propagate through the universe. You can swing a laser pointer across the moon faster than light, but no part of that motion carries information. That's the crucial difference. Now let's explore some of the most compelling ideas and challenges to the light speed limit. The most famous candidate is the tachyon, a hypothetical particle that is always faster than light. Unlike anything in the known universe, a tachyon wouldn't need to accelerate past the limit. It would be born beyond it. According to certain mathematical solutions in special relativity, tachyons could exist with imaginary mass and superluminal velocity, but allowing such particles into physical reality creates an immediate and serious problem. Causality breaks down. When something moves faster than light, different observers may disagree on the order of events. One might see a cause followed by an effect. Another might see the effect happen before the cause. If that becomes possible, paradoxes arise. You could receive a message before it's sent. You could prevent an event that has already occurred. Time loops. Logic collapses. Because of this, tachyons, while mathematically intriguing, are generally treated as non-physical, theoretical artifacts,
not real particles. But the search for superluminal phenomena doesn't stop there. Another contender is quantum entanglement, a phenomenon in which two particles become linked, so that the state of one instantly reflects the state of the other, no matter the distance between them. Measure one, and you instantly know the result of the other. At first glance it appears to violate the speed of light, but in truth, no usable information is transmitted. The outcome of each measurement is random. Only when the results are later compared using slower-than-light communication do the correlations become clear. Entanglement is strange, profoundly strange, but it does not allow faster-than-light messaging. The universe remains consistent. The law stands. Still, physicists haven't stopped imagining clever workarounds. One of the most well-known is the Alcubierre warp drive, proposed in this theoretical idea, grounded in Einstein's general relativity, suggests that a spacecraft could remain stationary within a bubble of spacetime, while the space in front of it contracts, and the space behind it expands. The ship doesn't move faster than light locally, but the bubble itself, and everything within it, could effectively move across vast distances at apparent superluminal speeds. It's not quite violating relativity, it's more like sidestepping it. However, there's a catch, a massive one. The Alcubierre drive requires something physics has never observed: negative energy, or exotic matter, with properties opposite to anything we know. It's unclear whether such matter can exist, and even if it did, the energy required to create and sustain a warp bubble might exceed the total mass energy of entire stars. Moreover, questions remain about the bubble's stability. Would it collapse catastrophically? Would it isolate the ship from the outside universe? Would causality still hold within or across its boundaries? The mathematics say maybe. Reality says not yet. According to the theory of cosmic inflation, in the earliest fractions of a second after the Big Bang, space itself expanded faster than the speed of light. Galaxies weren't flying apart through space. Space itself was stretching between them, carrying matter with it. And this, crucially, does not violate relativity. The speed limit applies to objects in space, not to the expansion of space itself. Even today, galaxies far enough away appear to recede from us faster than light, not because they're moving through space that quickly, but because space is still expanding. Light emitted from them now may never reach. They have crossed a cosmic event horizon, a boundary beyond which information cannot return. So in a way, faster than light motion is happening all around us, just not in the way we imagined. The lesson is subtle but profound. Every time we seem to glimpse something faster than light, nature finds a way to preserve causality. Quantum entanglement doesn't send messages. Warp drives require impossible matter. Cosmic inflation doesn't violate the rules, because it redefines the frame in which motion happens. The universe is clever. It allows strange behaviors, warped geometries and mind-bending probabilities. But it always protects the speed of light as the ultimate limit for any causal influence. So can anything go faster than light? Not in any way that lets us break causality. Not in any way that lets us skip across time, like stepping stones in a stream. The speed of light remains the boundary between what can be known and what must remain unknowable, between the reachable and the unreachable, between logic and paradox. And while we continue to imagine, to dream, to theorize, the universe keeps whispering its quiet, constant answer: this far, and no further. Chapter 12. Tachyons, Hypotheticals, and Science Fiction. There are particles we have measured, and particles we have predicted, but then, there are particles that exist only in the margins of theory, born not from observation, but from imagination. Tachyons, balloon. Tachyons are hypothetical particles that, according to certain mathematical interpretations of Einstein's special relativity, always travel faster than light. They do not accelerate past the limit. They exist beyond it from the start. They cannot slow down to light speed, just as we cannot speed up to reach it. In the realm of equations, tachyons are not forbidden. They arise as possible solutions when exploring what happens if you give a particle an imaginary mass, a mathematically valid but physically strange quantity. Their velocities would always exceed the speed of light, but allowing such particles into reality
opens a gateway to problems far more serious than just unusual speed. Because if a tachyon could transmit information, if it could carry a message, then causality itself would break. In Einstein's universe, time is not absolute. It depends on the observer's frame of reference. When an object moves faster than light, the sequence of cause and effect can reverse depending on who is watching. A message might arrive before it's sent. An outcome might precede its trigger. One observer sees a consequence, another sees a contradiction. The deeper you explore this possibility, the worse it gets. If information can travel faster than light, then paradoxes become unavoidable. You could cancel a message after receiving it. You could receive knowledge of an event before choosing to cause it. You could destroy your own future, or your past. These are not just storytelling devices, they are logical fractures in the structure of spacetime. And for that reason, most physicists treat tachyons as mathematical artifacts, theoretical ghosts, that serve to mark the boundaries of what must never happen. They are useful in calculations, they are interesting to study, but they are not expected to exist. Even so, tachyons have found a home, not in particle accelerators or cosmic rays, but in science fiction. Across decades of stories, they have become stand-ins for faster-than-light communication, time travel, and telepathy. Tachyon beams carry emergency signals through wormholes. Ships chase tachyon trails across quadrants. Time itself gets rewritten by waves of tachyon interference. Writers embraced what physicists rejected, and in doing so, gave the tachyon new life, not as a particle, but as a symbol, a shorthand for possibility, a question mark in motion. Because the truth is, the fascination with tachyons isn't really about physics, it's about the desire to overcome limits. In a universe where light speed defines the edge of influence, tachyons represent the dream of breaking free, the fantasy of crossing the galaxy in a breath, the hope of speaking to someone who is gone, not just far away, but beyond the reach of time itself. When science fiction reaches for tachyons, it's not making a claim, it's making a wish for closeness, a wish to reverse what has already passed. And that's why, even if they don't exist, tachyons matter. They mark the psychological edge of the light speed limit, the place where we stop calculating and start longing. They draw a line between what is measurable and what is imaginable. But the universe, so far, has refused to cross that line. No particle has been observed moving faster than light. No signal, no experiment has revealed a tachyon, despite decades of searching. And so, in place of discovery, we have understanding. We understand that the speed of light is not merely fast. It is sacred, not in a mystical sense, but in a structural one. It is what keeps time moving forward, what keeps cause ahead of effect, what keeps the fabric of the universe from unraveling into paradox. And by contrast, tachyons help us appreciate the kind of universe we do live in, a universe where time has a direction, where distance creates delay, and where meaning is preserved because actions unfold in order. The fact that we cannot send signals into the past is not a flaw, it is a feature. It gives history its shape. It gives choices their weight. It gives every moment its place, one after another, in a sequence we can follow, remember, and make sense of. In the end, tachyons serve a purpose, not by existing, but by helping define the limits of what can. They live in equations, in thought experiments, and in the distant edge of imagination. And there, they remain, not as discoveries waiting to be confirmed, but as echoes of a question we will never stop asking: what lies beyond the speed of light?
Chapter 13. Causality, the law that light protects. If there is one law that every part of the universe seems to respect without exception, one rule that is never bent, never ignored, never broken, it is causality. This principle, which states that causes must precede effects, is so deeply embedded in our experience of the world that we hardly even think of it as a law. It simply feels like the natural order of things. A stone falls after it is dropped, thunder comes after lightning, a memory forms after the event that created it. But beneath that simple intuition lies a complex and carefully cursored system of relationships.
built and enforced by the fabric of spacetime itself. A system in which the speed of light is not merely a limit, but a guardian. Causality is what keeps the universe coherent. Without it, the very concept of history would collapse. If events could happen before their causes, if effects could ripple backward in time, then there would be no way to distinguish between a sequence that builds and a paradox that destroys. A person might be born before their parents met, a signal could arrive before it was transmitted, and an action might erase the very memory of the person who performed it. In such a reality, logic would crumble, and with it, any hope of understanding how the world works. The speed of light prevents this chaos from unfolding, not because it is fast, but because it is consistent. It is the one invariant across all frames of reference, the one quantity that does not change no matter how fast you move, where you go, or how you observe. When Einstein revealed that the speed of light is the same for all observers, he also revealed something far deeper, that time and space themselves must bend to preserve that constancy, and in doing so they ensure that causality remains intact. This protection is visualized most clearly in the concept of the light cone, a geometric structure used in spacetime diagrams to represent all the points that can be reached from a given event at or below the speed of light. At the center of the cone is the event itself. Everything within the cone's future region can be influenced by that event, and everything within the past region could have influenced it. But anything outside the cone lies beyond the reach of cause and effect. It is elsewhere, elsewhen, unable to touch or be touched. Light cones are more than diagrams. They are the blueprints of physical law. They define the boundary between what is possible and what is forbidden. They ensure that no information can leap ahead of its own origin, that no action can skip the line of time and rewrite history. And they do this by anchoring every event to the speed of light. Even in the strange world of quantum mechanics, where particles seem to appear out of nowhere, exist in multiple states at once, and influence each other across vast distances, causality remains preserved. The correlations we observe in quantum entanglement may be instantaneous, but they do not allow for faster-than-light communication. The randomness of the outcomes, the impossibility of choosing a particular result, guarantees that no usable message can travel ahead of a photon. The illusion of superluminal influence remains just that, an illusion. It is tempting to imagine a universe where causality could be bypassed, a world where a traveler could leap ahead and send a message to their former self, a society where decisions made in the future could inform choices in the past. Science fiction often plays with these ideas, not because they are plausible, but because they touch something deep within us, a yearning to rewrite regret, to reverse time, to undo loss. But in every case, those stories rely on breaking the very fabric that holds the universe together. They entertain us precisely because they are not real. In the real world, even gravity, the most powerful and far-reaching of the fundamental forces, respects causality. Gravitational waves, which ripple through space-time from the collisions of black holes and the explosions of stars, travel at the speed of light. They carry energy and information, but they do not outpace the photons that shine from the same events. They remain within the cone. They obey the structure. What this means, fundamentally, is that the universe has a built-in memory. Events are recorded in the fabric of space-time itself, stitched into the geometry in such a way that they cannot be erased or reversed. The sequence of moments, the ticking of clocks, the paths of particles, all of it is governed by the inviolable logic of cause and effect, guarded by the light-speed boundary. This is not just a constraint, it is a gift, because without causality there would be no science, no prediction, no experiment that could be repeated. If the future could influence the past, then results could change retroactively, evidence could dissolve, observation would become meaningless. But with causality we gain order, we gain structure, we gain the ability to understand and to build upon that understanding, and more than that, causality gives meaning to choice. It ensures that actions matter, that decisions unfold over time, that effort leads to consequence. A universe where anything could happen, in any order, might be more flexible, but it would also be meaningless. Chaos is infinite in possibility, but empty in purpose. Structure is what gives events weight. It is what gives life narrative.
The speed of light is what gives structure to time. It sets the maximum rate at which influence can spread. It defines the outer shell of your impact, the farthest your actions can reach, the widest your voice can carry. Inside that shell you shape your world. Outside it, the universe remains unaffected, for now. But over time, your influence radiates outward, one photon at a time, never exceeding the limit, but always expanding. Even now, at this very moment, light from your body, your breath, your movements is traveling outward. A faint thermal glow, an echo of your existence, stretches into the darkness. It will never reach the nearest star in your lifetime. It will never outpace a cosmic event, but it is real, and it moves with perfect obedience to the law. The beauty of causality is not that it restricts us, but that it anchors us. It gives us a place in time. It allows us to be part of a continuous thread, not random flashes of existence, but unfolding story. Every cause you set in motion begins a ripple that moves at light speed or less, touching only what it is allowed to touch, shaping only what it is permitted to reach. And this applies not just to particles or stars or waves. It applies to moments, to memories, to meaning. Every photon that reaches your eye comes from something that happened in the past. It is a carrier of history. It tells you not just what is, but what was. And every time you act, you contribute to the future, a future that will know you only through the effects you left behind. A footprint of motion, a trail of consequences, a line of light expanding outward. In this way, the speed of light is not simply a limit. It is a boundary that makes time possible. It is the line between now and then, between here and else, and it is the reason the universe can be known, explored and experienced with confidence. Without it, there would be no direction. Without it, there would be no law. Without it, there would be no story. Because a story, any story, must begin somewhere, and end somewhere, and move only forward in between. And that forward movement, that one-way journey is not enforced by force, but by light. Light draws the map. It defines the path, and with it, the universe unfolds, one moment after another, each one bound to the next, each one shaped by what came before. Causality is not simply a rule. It is the reason we can remember, the reason we can plan, the reason we can hope. And at its center, holding the line, drawing the boundary, and carrying the truth from one moment to the next, is light. Chapter 14. Light Cones and the Edge of Now. In a universe that stretches endlessly in all directions, both in space and in time, it can be difficult to imagine that anything is truly limited, and yet, there is a boundary drawn, not by walls or distances, but by the very structure of reality itself. This boundary is not built from stone or fire, but from logic and geometry, and it is traced by light. The moment an event occurs, a flash of light, the beating of a heart, the flicker of an electron, it defines a region in space-time, from which influence can radiate outward, and into which influence can flow. This region, both the future it can touch, and the past, that could have touched it, forms what physicists call a light cone. A light cone is not a metaphor. It is a precise mathematical shape, in four-dimensional space-time, and it is essential to understanding not just how light moves, but how causality itself is enforced. Imagine a single point in space and time, a location and a moment, perhaps the instant a star collapses, or a voice whispers a name. From that point, light spreads outward in all directions, forming an expanding sphere. Over time, that sphere grows, and if you plot its expansion in both space and time on a diagram, it traces a cone-like structure, narrow at the moment of origin, and widening into the future. That widening cone represents every point in the universe that could be reached by light, or by any causal signal from that event. But just as there is a future cone, there is also a past cone, one that narrows down toward that moment, containing all the locations and events that could have influenced it by sending a signal, by radiating a force, or by casting a photon. Together, the future and past light cones form a complete causal structure, defining what is connected to what can affect what, and what remains forever isolated. Everything outside the light cone of a given event is causally disconnected. It is part of what's called the elsewhere region, not in the past, not in the future, but too far away in space to matter, and too distant in time to be relevant. No signal from those regions can ever reach the event in time to affect it. No influence from the event can reach them in time to matter. They are real, but they are out of reach, not because they are hidden, but because the speed of light makes them unreachable. This structure is not optional, it is not flexible, it is not a product of technological limitation. It is written into the mathematics of space-time. Even if you had infinite energy, infinite ambition, or infinite imagination, you could not break free from the boundaries of your light cone. You cannot reach into your own elsewhere. You cannot receive what hasn't had time to arrive. You cannot influence what lies beyond your expanding shell of light speed possibility. Likewise, everything you do, every motion, every word, every change, casts a ripple into your future light cone. Your influence spreads outward at light speed, touching everything it can, reaching as far as time and space will allow. And while it may feel small, even insignificant, it is permanent, it is recorded, it cannot be undone. The cone, therefore, is more than a diagram. It is a personal signature of reality. It is the map of your potential. It shows you where you are, where you could go, and where you can never reach. It separates the past that shaped you from the past that never touched you. It divides the future you might affect from the future that will forever unfold without you. And yet, this structure applies to everything, not just people, not just planets, but to every atom, every photon, every gravitational wave. Every point in space-time has its own light cone, its own causal structure, its own window into what can and cannot be touched. These countless cones overlap, intersect, and merge, forming a vast, tangled web of possibility and impossibility, of cause and effect, of now and then. In this way, the universe becomes not just a space we move through, but a network of interactions, defined not by absolute time, but by whether one event can reach another within the speed of light. There is no single, universal now, no cosmic clock ticking in sync across galaxies. There is only locality, only causal. This is perhaps one of the strangest consequences of relativity, the idea that now is not universal, that two observers moving at different speeds, or living in different gravitational fields, will disagree on what events are happening at the same time. They will not agree on the present, but they will always agree on the light cone. They will always agree on what can cause what, and what cannot. And in this agreement lies the beauty of the system, because even though time itself bends, stretches, and warps, causality remains stable. The light cone preserves the order. It is the thread that holds together the fabric, no matter how the cloth may twist. And it is light, specifically, the constancy of its speed that draws that cone, that carves that boundary, that keeps the structure from tearing apart. This makes the speed of light not just a number, not just a velocity, but a law of protection. It protects the sequence of moments. It protects the story. It protects the difference between action and consequence, between memory and anticipation, between history and potential. Even more deeply, it gives meaning to boundaries. When you look into the night sky, you are looking not just across distance, but across time, across your past light cone, across the events that have had time to reach you. The stars you see are real, but what you see is their history. The galaxies at the edge of your telescope are visible not because they are happening now, but because their light, traveling for billions of years, has finally crossed into your cone. And as time moves forward, your cone widens. You see more, you reach further. The universe reveals itself to you at exactly the rate allowed. So while you may never travel faster than light, while you may never leap from place to place without crossing the in-between, your light cone is always expanding. Every moment of your life increases the size of the universe that is causally connected to you. You are not static. You are reaching always. And because of this, your story unfolds not in isolation, but in resonance with everything else. You touch more than you see. You influence more than you realize, and you are influenced by more than you know. In the end, the light cone is not a limit. It is a structure of connection. It tells you not what is forbidden, but what is possible. And within that possibility, vast, growing, and defined by light, your life, your thoughts, and your presence continue to ripple outward, quietly writing themselves into the story of time. Chapter 15. Black Holes.
where even light surrenders. There is perhaps no region in the universe more mysterious, more extreme, and more revealing of the deeper rules of reality than the space surrounding a black hole. An object so dense, so gravitationally intense, that even light itself cannot escape once it crosses the threshold, known as the event horizon. In these cosmic abysses, the very notion of movement, of time, of distance, and of causality is rewritten, bent to the will of gravity. And within that bending, we discover something crucial. The speed of light is not just a limit for motion, it is a boundary for knowledge, for influence, and for truth. To truly grasp the role light plays near a black hole, one must begin not at its core, but at its perimeter, the event horizon. Unlike a physical surface or wall, the event horizon is a geometric frontier, defined not by matter, but by space-time itself. It is the dividing line between what can still communicate with the outside universe, and what is forever cut off. Once something crosses this line, be it a particle, a photon, or an entire star, it becomes invisible and unreachable to any observer beyond. This is not because the object stops existing, or because light slows down. In fact, even inside a black hole, light continues to travel at the same constant speed, c, relative to its immediate surrounding. But what changes, dramatically and irreversibly, is the nature of the paths that light can take. The geometry of spacetime becomes so deeply curved that every possible trajectory for light, every possible future direction, points inward. There is no longer any away, there is only. For someone falling toward a black hole, this change is imperceptible. The event horizon is not a wall or barrier. They would feel no bump, no sudden jolt, no warning. They would simply cross the horizon and continue falling toward the singularity, the center of the black hole, where all known laws of physics eventually collapse into a mystery we cannot yet describe. But for an outside observer, someone watching from a safe distance, the picture is radically different. As the object approaches the event horizon, time appears to slow for it. Its movement becomes slower and slower, its light becomes redder and dimmer, and eventually it seems to freeze at the edge, fading away into darkness. The object never appears to cross the boundary, it only disappears asymptotically, vanishing into silence. This strange contrast, that crossing the horizon, is both instantaneous and eternal, depending on the point of view, is a direct consequence of the constancy of the speed of light. That constant speed doesn't just regulate how fast things move, it defines what motion is possible. And when gravity becomes intense enough to reshape those possibilities, it also reshapes the nature of space, time, and observation. The event horizon, then, is a surface drawn by light. It is the last contour, a light beam aimed directly outward, can still hover, frozen in place, before being dragged back in. It marks the limit of escape, the outermost point, from which light can still return to the wider universe. Beyond it, every photon is doomed to curve inward, to spiral deeper into the gravitational abyss, never again able to climb out. This boundary has profound consequences, not just for matter and energy, but for information. If nothing can escape from beyond the event horizon, then what becomes of the data contained in the falling object? Does it vanish? Is it destroyed? Or is it somehow preserved? These questions are not philosophical, they strike at the heart of physics, and for decades they have formed the basis of one of the great unresolved debates, the black hole information paradox. According to classical general relativity, anything that falls into a black hole is gone forever. Its information is lost to the outside universe, erased from the observable record. But quantum theory, the other great pillar of modern physics, insists that information cannot be destroyed. No matter how complex a process may be, the details of its origin must, in principle, remain encoded in some final state. And so, if black holes truly erased information, they would violate a fundamental rule of quantum mechanics. To reconcile this contradiction, physicists proposed a bold and astonishing idea, known as the holographic principle. According to this concept, all the information about the matter that falls into a black hole may not actually be lost. Instead,
It might be stored on the surface of the event horizon itself. In other words, the three-dimensional contents of a black hole could be fully encoded in a two-dimensional layer at its boundary, just as a hologram contains a three-dimensional image on a flat surface. This idea does more than patch a paradox. It suggests something much deeper about the nature of reality. It hints that our familiar notion of volume, of depth, of space filled with content, may be a kind of illusion. What we experience as a three-dimensional world might be the projection of information encoded on distant surfaces, a perspective that, while still controversial, has sparked an entire revolution in theoretical physics. Yet, even in this radical interpretation, the speed of light remains central. It is the speed limit that defines the horizon's shape, the condition that determines what can be stored, what can be emitted, and what can never be recovered. It draws the invisible line between what is accessible and what is sealed away. And while black holes seem to trap everything forever, they are not entirely silent. Thanks to the brilliant insight of Stephen Hawking, we now know that black holes can in fact emit radiation. This phenomenon, known as Hawking radiation, arises from quantum effects at the edge of the event horizon. Pairs of virtual particles constantly pop into existence near the horizon. Occasionally one particle falls inward, while the other escapes. When this happens, the escaping particle becomes real, and the black hole loses a tiny bit of its mass. Over incredibly long timescales, far beyond the age of the current universe, this slow leakage of radiation could cause the black hole to shrink and eventually evaporate completely. This process is unimaginably slow for stellar mass black holes, and even slower for supermassive ones, but it suggests a poetic possibility that even the darkest regions of space are not truly eternal, that even here, where gravity rules and light is captive, there is a whisper of release, a long, slow exhale of energy, governed, once again, by the universal speed limit. In this view, light becomes not just the victim of the black hole, but the vehicle of its undoing. Because Hawking radiation carries energy outward, and possibly information as well, it reminds us that the speed of light does not merely confine, it shapes, it governs, it defines the boundaries of what can happen, and it ensures that even in the most extreme situations, the rules remain consistent. In the end, the black hole becomes the ultimate expression of the speed of light's authority. It is the place where even light, the swiftest messenger in all of physics, finds itself unable to escape, where motion becomes geometry, where space becomes time, and where time itself collapses into a singularity, a point that we cannot yet describe, a mystery that awaits a deeper theory. And so, when we look into the blackness of a black hole, or rather when we look at the absence of anything returning from it, we are not witnessing chaos, we are witnessing perfect order, a silence enforced by law, a stillness sculpted by geometry, a boundary drawn, not in matter, but in meaning. The speed of light, once again, is the pen that draws the horizon, the ruler that defines the possible, and the guardrail that prevents the universe from unraveling. It ensures that even here at the brink of the unknowable, there is structure, and within that structure, we glimpse not the failure of physics, but its ultimate triumph.
Chapter 16. Horizons of Causality. Where light draws the line. In every direction we look, there exists a boundary, not of space, not of material obstruction, but of causality itself. This boundary is invisible, yet absolute. It is the horizon beyond which no message can be sent, no influence can reach, no information can pass. And it is not drawn by human hands or limited by technological shortcomings. It is drawn by light. This boundary is called the light cone. At every point in space-time, a cone emerges, forward and backward, representing all the possible directions in which light can travel, and thus, all the possible events that can influence or be influenced. If an event lies outside your future light cone, you cannot reach it. If it lies outside your past light cone, it cannot have reached you. These are not just abstract notions, they are the scaffolding of how cause and effect operate in the universe. Causality, the idea that one thing can lead to another, is one of the most intuitive principles we know. A spark ignites a flame, a voice travels through air, a star explodes and light eventually reaches Earth.
But every one of these processes relies on the simple fact that the signal or the energy or the wave conveying the effect cannot outrun light. This is what preserves the coherence of the universe. This is what prevents paradox. Now consider what it means to violate this principle. Imagine, for instance, that a signal could be sent faster than light. From one frame of reference, it might look as though the signal was sent and received normally, but in another frame, due to the effects of relativity, it might appear that the signal was received before it was sent. Cause and effect would reverse. The timeline would fracture. Loops would form, logical contradictions embedded in the fabric of reality. It is for this reason, more than any aesthetic of elegance, that physics demands the speed of light as a limit. It is not simply about velocity. It is about preserving the consistency of time itself. It is about ensuring that what follows can never precede, that what happens can never pre-happen, that events unfold within a comprehensible, coherent structure. The light cone is more than a limit. It is a filter. It tells us not only what we can do, but what we can know. It defines the field of observability. Anything outside our past light cone is fundamentally unknowable, not just in practice, but in principle. The universe beyond that cone may as well not exist, for it has not, and cannot touch. And the farther we look, the more pronounced this boundary becomes. In cosmology, we speak of the observable universe, a sphere centered around us, approximately 46 billion light-years in radius, defined not by the size of the universe itself, but by the distance light has had time to travel since the beginning. Anything beyond that radius, no matter how luminous or loud or explosive, remains hidden. As time passes, more light reaches us. Our cone expands, but the expansion of the universe complicates this simple growth. Space itself is stretching, and in many regions it stretches faster than light can cross. There are galaxies moving away from us faster than light, not because they violate relativity, but because space between us is expanding at such a rate. Their light will never reach. Their stories will remain untold. This introduces the concept of the cosmological event horizon, not the same as the black hole's boundary, but just as absolute. It is the distance beyond which light emitted now will never reach us, even given infinite time. It is the future limit of causality, the line that separates what we will ever be able to see from what we never can. And this is not just a feature of our observational tools. It is built into the universe. It is the cost of living in a cosmos governed by the speed of light and the accelerating expansion driven by dark energy. We are not merely bounded by light's speed, we are encased in a sphere defined by it. Yet within that sphere, an entire cosmos unfolds. Stars are born and die, galaxies collide, black holes merge, and all of this, though limited, is enough to fill our sky with wonder. We are not living in a prison, but in a curated museum, vast beyond comprehension, but still curated. What we can see is not all there is, but it is more than enough to inspire. This inspiration extends to how we model the future. When cosmologists predict the fate of the universe, they do so with the understanding that some parts will disappear from view, that communication will be forever cut off, that even light will fade. These are not pessimistic views, they are the sober projections of a light-bounded universe. So what do we do with this knowledge, that we live inside a horizon of causality? We explore it, we map its boundaries, we send signals and catch echoes and measure delays. We define our experiments so that nothing outruns information. We build observatories that catch light as ancient as time itself, and in doing so, we make the most of the finite field of influence we inhabit. We also meditate on it. Philosophers and poets have long pondered the boundaries of knowledge, the limits of experience. Now physics joins that tradition, not with metaphor, but with metric. The light cone is a physical expression of epistemology. It tells us where ignorance is not a failure of effort, but a consequence of nature. And even in that ignorance there is beauty, because to live within a light cone is to live within a story. There is a beginning, a middle, and a yet unwritten end. There are events we will witness, and those we never will. There are mysteries that will remain, not because we are inadequate, but because we are bound. But in that boundedness lies meaning. The speed of light does not make the universe smaller, it makes it legible. It turns infinity into narrative. It makes each star's light a message, each observation a moment. The horizon of causality is not a flaw, it is the signature of coherence. And we, bounded as we are, continue to reach, not to escape the light cone, but to understand its shape, to navigate its contours, to live fully within the space it allows. For within that space, all the wonders of existence unfold, and we are here to witness them.
Chapter 17: Time Machines, Paradoxes, and Light's Relentless Gait. The idea of time travel has long seduced both physicists and storytellers. The dream of stepping backward into the past, or leaping forward into the far future, haunts our imagination, fueled by science fiction and scientific speculation alike. But underneath the wonder lies a stern gatekeeper: the speed of light. It is not just a cosmic speed limit for particles, it is a fundamental boundary that constrains how events unfold, how influences propagate, and whether time itself can be manipulated at all. To understand why light plays such a pivotal role in discussions about time machines, we must examine what time travel would entail in the language of physics. In Einstein's general theory of relativity, space-time is not a static backdrop, but a dynamic fabric, curved by the presence of mass and energy. In theory, this curvature can be manipulated into exotic shape. Solutions like closed time-like curves, loops in space-time that return to their own past, do appear in the mathematics, but appearing in equations is not the same as existing in the real universe. One of the most famous such solutions is the Gödel metric, discovered by Kurt Gödel in 1949, which describes a rotating universe where paths through space-time could loop back in time. There's also the Tipler cylinder, an infinitely long spinning tube that could, in theory, bend space-time into a time machine. And then there are traversable wormholes, hypothetical tunnels through space-time that might allow instantaneous travel between distant points, or even different moments. All of these rely on extreme warping of space-time geometry, often requiring negative energy or exotic matter to stabilize. But even in these speculative constructs, light remains the enforcer of causality. No influence can move from one point to another faster than a beam of light would. Even when space-time itself is twisted or curved, even when a tunnel or loop appears possible, the light cones, those invisible zones that define the future and past of each event, must remain unviolated. If any motion allows information to travel outside its light cone, paradoxes emerge. And paradoxes are more than puzzles. They are threats to coherence. The grandfather paradox, where a time traveler prevents their own existence, is not merely a narrative twist, it is a breakdown of cause and effect. If such contradictions could happen, the universe could not maintain a consistent history. And so, most physicists believe that some deeper principle, perhaps not yet fully understood, must prevent time machines from functioning. Many suspect that the answer lies in quantum gravity or in the still unified laws of information and geometry. But until then, the speed of light acts as a built-in safeguard. Stephen Hawking once proposed the chronology protection conjecture, a tongue-in-cheek name for a serious idea that the laws of physics conspire to prevent time machines. According to this view, any attempt to build a closed time-like curve would self-destruct due to quantum effects or instabilities. Light, as always, plays a central role. Any disturbance in space-time would need to be transmitted through radiation, through light, and any feedback loop of light traveling backward in time would grow infinite, creating a breakdown rather than a portal. There is also the issue of energy. Manipulating space-time enough to create a time machine would require vast, possibly infinite energy. The constraints imposed by light speed do not only cap how fast things can travel, they limit the kind of space-time configurations that can even form. Exotic matter, negative energy density, and quantum vacuum states all exist in theory, but they remain unproven in practice. And as long as no known material or field can be arranged to support such configurations, time machines remain mathematical ghosts. More subtly, even the concept of simultaneity of now dissolves under relativity. Two observers moving at different speeds will disagree about what events are happening at the same time. This fluidity of the present means that time is not a universal flow,
but a personal one, shaped by motion and gravity. Light signals are what determine these slices of time. When one event can send a light beam to another, they can be connected. Otherwise, they remain causally isolated. And so, time is not a stage we move across, but a path carved by light. Even quantum mechanics, with all its strangeness, does not offer a loophole. Entanglement allows particles to correlate across vast distances, but not to communicate faster than light. The no-signaling theorem ensures that information cannot be sent backward through time, preserving the order of events. Every quantum fluctuation, every probability wave, still respects the overarching structure imposed by light speed. It is the thread that binds the quantum world to the classical one, keeping causality intact. Ultimately, the dream of time travel is a mirror that reflects our desire to break free of sequence, of consequence, of constraint. But the universe answers with elegant resistance. It offers complexity, curvature and curiosity, but not contradiction. Light remains the arbiter, ensuring that time moves with order, that causes remain before effects, and that the universe retains a coherent narrative. In the end, time machines may remain fiction, but in their impossibility, they illuminate the depth of what time really is. Not just an axis on a graph or a ticking of seconds, but a flow sculpted by light. Every second you live, every moment you remember, every future you await, is stitched together by the same law that nothing outruns a photon. And within that constraint, the universe finds its voice, its structure and its continuity. So when we ask why time machines are forbidden, the answer may be as simple and as profound as this: because light says no. And in the silence that follows, time continues, steady, irreversible and just out of reach.
Chapter 18. The Cosmic Speed Limit. Why nothing can go faster. The universe is vast and expanding, but no matter how fast galaxies recede from one another, no matter how deep into space we peer, one principle holds: nothing can travel faster than light in a vacuum. This is not a technological limit. It is not a failure of propulsion or engineering. It is a structural rule of the cosmos, a boundary written into the equations that describe motion, energy, and information. And understanding why that boundary exists is to understand the scaffolding upon which reality is built. First, it must be understood that the speed of light is not simply the speed of light. It is the speed of causality, the fastest that any influence, any signal, any effect can move from one place to another. In physics, this number, approximately 29th sound in 792,438 meters per second, is more than a measurement. It is a conversion factor, tying together units of space and time. In the equations of relativity, c appears not as a speed, but as a constant that transforms how motion and time are experienced depending on one's frame of reference. The reason nothing can go faster is woven into the geometry of space-time. As an object accelerates toward light speed, its energy increases dramatically. According to Einstein's famous equation, E immense, mass and energy are interchangeable. As a particle's speed increases, so does the energy required to push it faster. The closer it gets to c, the more energy it takes, and this energy demand grows without bound. At light speed, the energy required becomes infinite, and no object with mass can attain infinite energy. Thus, the speed of light is not merely a barrier, it is a horizon that cannot be crossed. Photons, which are massless, are allowed to move at this speed because they were born into it. They do not accelerate to c, they exist at c. But any particle with mass would have to undergo infinite acceleration to join them, and this is physically forbidden. No known field or force can provide the energy necessary to make that transition. It is not a practical limitation, it is a categorical one. More than just a rule about velocity, this limit preserves causality. If faster than light travel were possible, an effect could precede its cause. Two observers could disagree about the order of events, and in some frames of reference, a message could arrive before it was sent. This is not just a matter of confusing chronology, it is a collapse of logic. The laws of physics are structured to avoid these contradictions, and the speed of light is the firewall that keeps temporal coherence intact. Some speculative theories, involving hypothetical particles called tachyons, or the manipulation of space-time through wormholes,
have suggested ways around the light speed limit. But every such proposal either requires unverified forms of matter or violates other known laws. In practice, no experiment has ever shown a violation of even quantum entanglement, which correlates particles instantly over distance, does not transmit usable information faster than light. The no signaling principle still applies. Reality stays consistent. The light speed barrier also ensures the integrity of energy conservation. As an object moves faster, not only does its energy rise, but its effective mass increases from the perspective of an external observer. This dynamic scaling ensures that relativistic momentum and kinetic energy remain balanced. If something could leap beyond these balances would break, and the fundamental conservation laws would no longer hold. But rather than being a limit to lament, the cosmic speed limit provides a foundation on which order is built. It makes the universe readable, predictable, and narratively coherent. It allows galaxies to evolve without collapsing into informational chaos. It defines the shape of spacetime, the paths that light takes, and the boundaries of what we can know. Without this constraint, there would be no symmetry, no reliable physics, no continuity across observers. Everything would be disconnected from everything else. In this light, the speed of light is not a cage, but a frame. It is the quiet architect of cosmic order. Every law that governs motion, from Newtonian inertia to quantum probability, bows to it. It provides the rhythm to which time beats and the ceiling beyond which matter dares not aspire. It shapes the evolution of stars, the dance of planets, the trajectory of photons that fill our skies with starlight. So when we say nothing can go faster than light, we are not confessing a failure. We are affirming a symmetry, a consistency, that holds from the smallest particle to the largest galaxy. This unbreakable rule is not merely observed, it is the reason anything can be observed at all. The universe, in its wisdom, enforces this speed limit, not out of cruelty, but out of necessity, and within its bounds, a cosmos of wonder unfolds, connected, coherent, and constantly become. Chapter 19, The Light Barrier and the Edge of Causality. Across the grand expanse of cosmic history, there exists a persistent tension, a tension between what can be known and what lies just beyond the grasp of discovery, between what moves and what signals that movement, between action and the light that carries its news. At the heart of this dance stands the light barrier, a principle not imposed from above, but rising from within the very structure of space and time itself. It is not a wall we are pushed against, but a mirror that defines where cause ends and where consequence may begin. To explore this boundary is to step into the edge of causality, the zone where every action must respect a precise choreography laid out by the fabric of the universe. The speed of light does not merely limit how fast objects can move, it determines the order in which things can occur. This order, this cosmic timeline, is upheld not by decree, but by necessity. Without it, the narrative of the universe unravels, and the past could blend into the future in ways that defy logic, memory, and meaning. It begins with a simple truth. Light moves through vacuum at a fixed speed, unchanging across all frames of reference. Whether you run toward it or away, the light you measure always obeys the same rule. This universality is not a feature of light alone, but of how space-time is stitched together. When we speak of events, a supernova exploding in a distant galaxy, a message transmitted across a radio wave, a photon striking a sensor, we are speaking of nodes in this interconnected web, and their placement is governed by whether one can influence another without violating the light speed boundary. This brings us to the concept of the light cone, a shape in four-dimensional space-time that outlines the region of influence an event can have. Anything inside the cone can be reached or affected by signals from the event. Anything outside it lies forever inaccessible unless the rules change. And the rules do not change. No signal, no matter how clever, no matter how abstract, has been shown to pierce the light cone from the outside. This barrier is not physical in the ordinary sense. You cannot touch it, see it, or cross it in a spaceship, but its consequences are more real than any wall. When scientists imagine manipulating the light barrier, they encounter resistance not from materials or technologies, but from mathematics itself. The equations of special relativity do not merely warn against surpassing light speed, they break when asked to compute it. Denominators vanish, times stretch into infinities, mass balloons into impossible numbers, and space-time, that supple arena of gravity and inertia, refuses to accommodate anything beyond that upper bound. If a theory permits superluminal motion, it must be modified so deeply that it loses its predictive power, and no such theory has ever succeeded. There are deeper layers still. Information, that delicate thread from which consciousness, computation, and communication are all spun, must also obey the light barrier. A thought cannot travel faster than a flash, a pattern of bits cannot outpace a beam. This ensures that knowledge cannot leap ahead of cause, that a decision cannot outrun the conditions that birthed it. It protects not only the flow of events, but the sanctity of logic itself. What if we could break this rule? What if the light barrier were simply a challenge, waiting to be overcome by some clever trick or undiscovered particle? Theoretical constructs like tachyons, hypothetical particles that always travel faster than light, have been explored on paper, but they come burdened with baggage. They violate energy conservation, they destabilize quantum fields, they suggest backward time travel, and impossible feedback loops. No evidence for them has ever surfaced, and most physicists regard them as mathematical artifacts, not entities of nature. Yet the question persists, because our longing persists, a longing to reach farther, to act faster, to escape the crawl of time and leap into the future or dart into the past. But the universe seems to resist this temptation at every turn. Wormholes that might offer shortcuts remain unstable or fantastical. Quantum teleportation transmits correlations, not substance. Entanglement teases us with its strangeness, but always denies us a true signal. Each door to faster-than-light motion closes, not with a bang but with a whisper of deeper lore. In this light, the barrier is more than a limit. It is a filter. It allows complexity to unfold in an orderly way. It lets stars burn, planets orbit, cells divide, and minds form without being overwhelmed by a torrent of conflicting signals. It gives evolution time to work. It lets galaxies maintain structure. It slows the diffusion of chaos, and in doing so it grants the universe not only stability, but beauty, the kind of beauty that requires rhythm, pacing, and space for surprise. Causality is not just a feature of physics, it is the frame within which consciousness can emerge. For awareness to develop, for thoughts to connect, for actions to have meaning, there must be a structure that enforces direction, a before and an after. The light barrier is what ensures that structure. It enforces the line between cause and effect, between message sent and message received, between story and noise. And so we arrive at the edge of what can be known, not because we lack the tools, but because the tools themselves are bounded. Every telescope, every detector, every particle collider, reaches out at light's pace. Every data stream we capture from deep space is already ancient by the time it arrives. We are time travelers in reverse, catching echoes of what has been, never quite touching what is. Yet within that limitation lies the possibility of understanding, because the very predictability that the light barrier enforces allows us to decode the universe's past, to model its future, and to dream about what lies in between. The speed of light in setting a final constraint also creates a canvas. Upon it, the cosmos paints with photons, sculpting shadows, and sending messages across the stars. So when we look up, waiting for the glow of a dying star or the flicker of a distant galaxy, we are not witnessing delay. We are watching the law in motion. The light barrier does not hide the universe from us. It reveals it, one moment at a time, with perfect discipline. And in this discipline, in this constraint, we find the very pulse of reality. Chapter 20. The Illusion of Instantaneity. It is tempting to think of light as instantaneous, as something that travels so swiftly, that for all practical purposes, it might as well be immediate. We flip a switch, and the room fills with light. We gaze up at the stars, and they seem to shimmer in the now. Our eyes, so attuned to the visible spectrum, often fail to register the delay, the journey, the patient transit of photons through time and space. But this illusion is only that, an illusion, because in truth, light is not instantaneous, and its finite speed imposes a subtle but universal delay on everything we see, everything we know, and everything we think we understand. Every observation we make is, in some measure, a view of the past. When we look at the moon, we see it not as it is, but as it was 1.3 seconds ago. The sun's light takes more than 8 minutes to reach us. The nearest star system, Alpha Centauri, beams us photons that departed over 4 years ago. And the light from the Andromeda galaxy, visible on a clear night as a smudge in the sky, began its voyage more than 2 million years before it entered your eye. These delays are not errors or imperfection. They are the consequence of light's finite speed, and they shape the very texture of perception itself. Our modern technology has narrowed these gaps for local communication. Fiber optics and radio waves zip data across the globe at near light speeds, yet even here, the delay exists. A signal from Earth to the Moon takes over a second each way. Mars, minutes. To the outer planets, hours. There is no real time across the solar system. Even the fastest signals carry the weight of lag, of waiting, of time already spent. And at cosmological scales, the delay becomes transformative, turning the sky into a museum of ancient light. This raises a fascinating paradox. We never see the universe as it is, we only see what it was. Every point of light in the sky is a relic of an earlier state. Our most powerful telescopes are not merely seeing farther, they are seeing deeper into the past. The James Webb Space Telescope, for example, is not just snapping images, it is unearthing the infancy of galaxies, capturing photons that began their journey near the dawn of time. The farther we look, the older the light becomes, and so, in reaching outward, we also reach backward. This delay is not merely an observational curiosity, it is foundational to how knowledge accumulates. We must constantly correct for this lag, not just in astronomy but in particle physics, GPS technology and satellite communication. Signals must be time-stamped and synchronized across reference frames. Equations must be adjusted to account for when and where an event actually occurred, versus when it was observed. The finite speed of light is not a footnote, it is a constant that every calculation must respect. More profoundly, the illusion of instantaneity shapes how we think about reality. We assume a shared present, a universal now, that binds us together, but in relativity, this notion dissolves. Two observers in motion, relative to each other, will disagree about what events are simultaneous. For someone speeding past at near light velocity, your now and their now are not the same. The faster you go, the more time and space entwine, and the very concept of a present moment fracture. This means that what is happening now, for you is not happening now for someone light years away. Your moment of reading this, the shape of your thoughts, the beat of your heart, occurs in a different temporal frame, from events in distant galaxies. And yet all of these disparate slices of time coexist, stitched together by light. It is light that draws the lines of connectivity, the bonds between moments. It is light that determines what can influence what, and when, and how. The illusion persists because we live in a bubble, a local zone where the delay is negligible, where lights flicker on, and voices respond, and actions appear to ripple outward without pause. But this immediacy is a trick of scale. At broader levels the delay stretches. The cosmos reveals itself not all at once, but in waves, in echoes, in messages delivered at the cosmic speed limit. The deeper the distance, the older the light, the wider the gap, the more fractured the notion of now becomes. Philosophically, this raises deep questions about what it means to exist. If we only see things as they were, do they exist, for us as they are? Is the reality we perceive a reconstruction, a simulation built from lagging photons? In some sense, yes. Our understanding of the universe is an act of interpretation, a decoding of delayed signals. And yet, because those signals obey strict laws, because light moves at a constant speed in vacuum, because time dilation and Lorentz contraction are well defined, we can trust the reconstruction. We can piece together the unfolding of time,
with extraordinary accuracy. This trust is what makes science possible. It is what allows engineers to guide spacecraft through the solar system, what allows astronomers to map the universe, what allows physicists to reconstruct collisions inside particle accelerators. The delay does not prevent knowledge, it demands precision, and that precision is what gives rise to clarity. Still, there is something poetic in the idea that we are always looking into the past, that even in the present, we are surrounded by memories made visible. Every star we see is a memory, every color we perceive is a story in transit. Every reflection, every glint, every shimmer is a history book written in photons, and we, the observers, are not passive. We are participants. We add to the web of signals emitters in our own right, sending our own light outward, forever. And so, when we speak of the illusion of instantaneity, we are really speaking of the grace with which light binds the universe together. It does not rush, it does not cheat, it moves with perfect regularity, delivering truth with a slight delay. And in that delay, in that cushion of time between action and awareness, between event and observation, lies the space for thought, for reflection, for wonder. To live in a universe where light has a speed is to live in a universe where discovery is always unfolding, never complete. We chase the light, and in doing so, we chase meaning. We wait for the next burst, the next echo, the next flash in the dark, and each one arrives not when we want it, but when the cosmos permits, right on time, never late, never early, always traveling at the exact pace that nature allows. And in that punctuality, in that elegant restraint, we find not limitation, but invitation, a universe not too fast to grasp, not too chaotic to follow, but perfectly timed for minds like ours to wonder, to explore and to see.
Chapter 21. The Photon's Journey, a Life Without Time. Of all the travelers in the cosmos, the photon stands apart. Massless, timeless, and relentless, it carries light across unimaginable distances, slipping through the fabric of space as if it were water flowing across glass. It is the messenger of the universe, the bearer of sight and signal, the particle that defines the edge of causality. But what does it mean to live at the speed of light? What is a journey when time does not pass? What is distance when space and time no longer behave as we expect? To the photon, time does not exist. It is not simply that time moves slowly or that clocks tick differently in the photon's frame. Proper time is zero. The moment a photon is emitted and the moment it is absorbed are, from its perspective, the same moment. There is no intermediate state, no path taken, no duration endured. The entire voyage, whether across a centimeter or a billion light-years, collapses into a single, indivisible instant. This idea is not poetic metaphor. It is a direct consequence of Einstein's theory of special relativity. Proper time, the time measured by a clock traveling alongside an object, depends on the object's velocity. As that velocity approaches the speed of light, proper time slows. For a massless particle traveling exactly at light speed, that proper time vanishes entirely. The photon does not age, it does not experience, it simply exists, at both ends of its path, simultaneously, from its own perspective. To us, of course, the journey is very real. We detect the photon at one point, and we can trace its source back in time and space. We see it arrive, we measure its wavelength, we infer its energy. But all of these properties emerge only in our frame of reference, a frame anchored by the slow tick of time and the resistance of mass. To us, light moves. To the photon, there is no motion, there is only connection. This contradiction that a thing can travel without traveling, move without duration, connect without crossing, is one of the deepest mysteries in modern physics. It is a window into the strangeness of relativistic frames, into the malleability of time itself. For if time can vanish from a particle's perspective, what does that say about the nature of time? Is it a substance, a direction, a byproduct of motion, or is it simply a framework, emergent from relationships between entities, without independent reality. The photon's journey also speaks to the strange duality at the heart of quantum mechanics. Is the photon a wave, spreading out in interference and diffraction, or is it a particle, a point-like burst of energy exchanged in discrete quantum? The answer is both, and neither, depending on how you measure it. And in that ambiguity lies the photon's power, its ability to carry both energy and information, both clarity and uncertainty, from one place to another. When a photon is born, say from the heated surface of a star, it emerges from a chaotic dance of charged particles. It escapes the electromagnetic prison of dense matter, carrying away a tiny piece of energy, a tiny note in the star's symphony of light. It may travel billions of years through the cold darkness of space, untouched and unperturbed, until at last it reaches a planet, a telescope, an eye, and in that moment of arrival, it imparts its message, a whisper from a time long gone, a glimpse into a place far away. Yet for the photon there was no darkness, no distance, no waiting. The emission and absorption are bound as one, and this suggests something profound, that the universe is not stitched together by continuous processes unfolding in time, but by relationships that span time entirely. The photon links two events, a beginning and an end, as if they were adjacent, regardless of the space between. This perspective radically alters our conception of what motion and existence mean. For the photon, the cosmos is not a vast arena to traverse, but a web of connections to instantaneously embody. Its life is not a path, but a pair of endpoints. And yet this simple act, linking origin to destination, allows for everything we see. All of vision, all of observation, all of interaction between distant entities, arises from the countless photons making these instantaneous leaps, unseen from their own perspective, but visible from ours. One might then ask, is the photon's experience or lack thereof unique? What does this say about the very fabric of reality? Could time, as we know it, be an emergent property, arising only for beings that move slower than light? Could our perception of before and after be a byproduct of our inability to reach the speed where such distinctions vanish? If so, then the photon offers not just illumination, but liberation, freedom from time, from sequence, from becoming. But even as it transcends our experience of time, the photon remains bound by certain constraints. It always moves at the same speed in vacuum. It is affected by gravity, not because it has mass, but because space-time itself bends, and the photon must follow the curve. This bending, observed in phenomena like gravitational lensing, reveals that even timeless entities are subject to geometry. The shape of the universe still dictates their path, even if they do not feel the passage. Moreover, photons cannot exist alone. They are born from interactions and they die in absorption. They are not permanent actors but transitional events, messengers without memory. Their existence depends on the world of mass and charge, the world of beginnings and endings. Without atoms, stars and sensors, there would be no photons. Without observers, there would be no stories for them to carry. In this way, the photon's journey is a metaphor for all interaction. Connection without motion, presence without passage, information without delay. It shows us that even in a universe ruled by time, there are entities that transcend it, not by ignoring it, but by living on its boundary, by tracing its outlines without stepping inside. And so the photon remains our silent companion, threading the cosmos with invisible lines, linking past to present, origin to destination. It is the rhythm of the universe, not in ticking seconds, but in flashes of meaning. It is the thread by which the cosmos speaks, not to itself but to us. And in listening, in seeing, in decoding the messages carried by light, we are not merely spectators, we are part of the fabric being woven. To understand the photon is to glimpse a world without clocks, without duration, without motion, a world where presence is instantaneous, and knowledge is direct. It is a world that lies behind the veil of our perception, but one that shapes everything we know. For in every glimmer of light, there is a silent story, told by a traveler that knows no time, only connection. And in that connection, we find not just illumination, but revelation. Chapter 22.
the geometry of light's path. In the vast theater of the cosmos, the motion of light is not merely a journey from one point to another. It is a dialogue between the traveler and the stage. Photons do not simply traverse space. They are guided, bent, shaped and redirected by the very geometry of space-time itself. In the absence of mass, they still possess momentum. In the absence of force, they still follow curves. Their trajectories reveal the invisible contours of the universe, illuminating not only the objects they encounter, but the space through which they pass. This geometry is not Euclidean. It is not the tidy, flat structure we once imagined, where straight lines stretch forever and parallel lines never meet. Instead, the universe is warped. It bends around mass and energy, stretches under the influence of expansion, and twists in the presence of angular momentum. The path of light is always straight, in the sense that it follows a geodesic, the shortest possible path in curved spacetime, but that straightness can appear crooked to an external observer. Consider the phenomenon of gravitational lensing, where the light from a distant star or galaxy is bent around a massive object, such as a cluster of galaxies or a black hole. This is not a distortion of the light itself, but of the space-time it travels through. The massive object warps the space around it, like a heavy ball on a rubber sheet, and the light follows the curve of that deformation. The result is a bending of the light's path, an apparent displacement of its source, and in some cases the creation of multiple images of a single object. This effect is not theoretical. It has been observed countless times, from the first confirmation during a solar eclipse in 1919, which helped establish general relativity, to modern surveys using the Hubble Space Telescope. These cosmic mirages are not merely curiosities, they are tools. By analyzing the way light is bent, we can map the distribution of dark matter, estimate the mass of galaxies, and peer deeper into the early universe than would otherwise be possible. Even in less extreme conditions, space-time curvature plays a role. The light from the sun is redshifted as it climbs out of the solar gravitational well. GPS satellites must adjust at the slight warping of time between Earth's surface and their orbital paths. Every photon's journey is affected, subtly or dramatically, by the geometry through which it moves. And in this sensitivity, light becomes a probe, not just of object, but of the structure of space itself. This interaction between light and geometry extends beyond gravity. In cosmology, the expansion of the universe stretches space itself, and with it, the wavelengths of light. A photon emitted when the universe was young and dense arrives today, redshifted, its energy diminished not because of resistance or collision, but because the very metric of space has changed beneath it. This cosmological redshift is a window into the history of the universe, a record of its growth encoded in the color of its oldest light. To truly understand the geometry of light's path, we must also consider the role of the observer. What appears as a straight line in one frame may appear curved in another. What seems to move forward in time for one may appear delayed or even simultaneous for another. These relativistic effects are not illusions, but the result of space-time's flexibility, a flexibility that bends not just the path of light, but the very framework of causality and simultaneity. At the heart of this framework lies the concept of the null geodesic, the path traced by a photon through space-time. Unlike the world lines of massive particles which follow time-like paths and accumulate proper time, null geodesics exist at the boundary. They mark the transition between what can be reached and what cannot, what can influence and what must remain isolated. The photon's journey defines the edge of the light cone and therefore the edge of causality, and yet, this path is not chosen, it is dictated. Given a starting point in a direction, the path of light is inevitable, governed entirely by the metric of space-time. Change the mass distribution, and the path will change. Shift the expansion rate, and the redshift will shift. The photon does not resist or adapt, it obeys. Its simplicity is what makes it powerful, its lack of mass is what makes it revealing. It is the perfect follower, tracing the shape of space without altering it. This quality gives rise to another insight, that light is the universe's way of exposing its own shape. Massive objects distort space, but they do not reveal that distortion directly. It is the light passing nearby or through that discloses the warp. It is the photon's behavior that turns invisible curvature into visible consequence. Every lensing arc, every shifted spectrum, every delayed signal is a clue a fingerprint of the geometry beneath. In this sense, light becomes more than a tool of vision. It becomes the agent of revelation. It maps the unseen. It charts the uncharted. It carries not only the appearance of object, but the structure of the void between them. The photon's journey is thus a cartography of curvature, an etching of space-time's shape into our instruments and into our understanding. This mapping extends to the largest scales imaginable. The cosmic microwave background, the afterglow of the Big Bang, is not a smooth sheet of light. It is dimpled and rippled by the density variations and gravitational wells it has passed through. These anisotropies are not flaws. They tell us how matter was distributed in the early universe, how it clumped and grew, how it seeded the galaxies we see today, and all of this comes from the geometry written in the photon's path. So when we consider the speed of light, we must remember that its constancy does not imply rigidity. Light does not demand a flat road. It moves as space permits, straight in curved space, bent in distorted time, always faithful to the terrain it crosses. It is a traveler without protest, and in its silence it speaks volumes. The geometry of light's path is the language of the cosmos. It tells us where mass lies, how energy flows, how space expands and how time bends. It is not merely the light we see, but the way it moves, that reveals the shape of everything. And in following its curves, we do not just learn about stars and galaxies, we learn about the invisible skeleton of the universe itself. In the bending of light, we see the bending of reality. In the delay of photons, we measure the stretch of time. In the distortion of images, we uncover the presence of the unseen. Light's path is not just a line, it is a message, and in reading that message, we come closer to understanding the frame upon which all of existence is drawn.
Chapter 23. The speed limit of the universe. When we speak of the speed of light, we are not merely referring to a fast-moving phenomenon. We are pointing to the ultimate speed limit of reality, a constant so deeply embedded in the laws of nature that it governs not only how fast something can move, but also how cause and effect relate, how information propagates, and how the fabric of space-time maintains coherence. The speed of light in a vacuum, approximately 299,792 kilometers per second, is not just fast, it is foundational. It is the border between what is physically possible and what lies beyond. Unlike other speed limits in everyday life, the speed of light is not enforced by external barriers or resistances. It is written into the equations that define our universe. It appears in Maxwell's equations for electromagnetism, in the structure of Einstein's relativity, in the very shape of the space-time manifold. Any attempt to exceed this limit results not in acceleration, but in the breakdown of predictability, in the inversion of causality, and the collapse of temporal order. To see why this is so, consider two events. If one causes the other, that cause must precede the effect within every valid frame of reference. But if information could travel faster than light, there would exist frames in which the effect could be observed before the cause, violating the principle of causality. This is not merely an abstract inconsistency. It would destroy the very logic by which the universe operates. Events would lose their temporal anchors. Outcomes could appear without precedent. The chain of reasoning that science depends on would unravel. This is why light speed is not just a speed, it is a boundary. It is the edge of influence, the outer rim of possible interaction. It defines the light cone, a region in space-time from which signals can reach a particular event. Outside that cone lies elsewhere, not just in space, but in a realm causally disconnected from the event in question. Light speed draws that line. Nothing can cross it outward from inside. Nothing can jump across it from outside. And yet within this constraint lies immense richness, because even though we cannot exceed the speed of light, we can approach it. We can observe how time dilates, how length contracts, how simultaneity dissolves. We can build accelerators that bring particles within whispering distance of light speed, and watch their clocks slow to a crawl. We can use the constancy of light to synchronize distant systems, to navigate the stars, to transmit information across the earth, in the blink of a moment. Indeed, the very technologies that define the modern world, GPS, fiber optics, satellite communication, rely on the unwavering constancy of light speed. The structure of the internet, the stability of our electrical grids, the functioning of atomic clocks, All of it depends on the predictable behavior of light. It is not merely a limit to what we can do. It is the scaffold upon which everything we have built rests. And still, we ask, why this speed? Why this particular value? Is it an arbitrary number, or does it arise from something deeper? Some physicists have speculated that the speed of light may be a ratio, the result of other fundamental constants combining in a specific way. In natural units, where constants like Planck's constant and the gravitational constant are set to 1, the speed of light also becomes unity. This suggests that its value may not be intrinsic, but relational, a reflection of how different aspects of the universe scale against each other. If this is true, then the speed of light is not merely a feature of light itself, but a statement about the structure of all things. It tells us how space and time cohere, how energy and momentum relate, how mass and information intertwine. It defines not just how fast things move, but how deeply they are allowed to change. This idea finds further support in quantum field theory, where particles emerge, not as standalone entities, but as excitations in fields that extend throughout spacetime. These fields respect the light curve. They respect causality. Their fluctuations are bounded by the speed at which information can propagate. This ensures that even in the foaming chaos of quantum uncertainty, the structure of reality remains intact. Still, the dream of faster-than-light motion persists. We wonder about warp drives, wormholes, and quantum entanglement. We imagine skipping across the cosmos in seconds, folding space like fabric. But even these speculations, if they are ever made real, must obey the deeper constraint that information must not outrun light. That cause must precede effect. That reality must remain consistent. This is not a limitation to resent. It is a framework to embrace. Because in setting boundaries, the universe also sets meaning. If light could move infinitely fast, there would be no delay, no unfolding, no discovery. Everything would be seen at once. Every action would touch everything. There would be no mystery, no sequence, no story. Time would collapse. Causality would dissolve. Instead, we live in a universe where light takes time to travel, where actions ripple outward at a fixed pace, where knowledge arrives step by step. This delay is not a bug. It is the space in which thought happens, in which meaning forms, in which we learn and explore. The speed of light creates room for wonder. It also creates boundaries that are not merely physical, but existential. The observable universe is finite, not because the cosmos has an edge, but because light has a speed. There are places we will never see, not because they do not exist, but because their light will never reach us. There are events happening right now that lie forever beyond our horizon, not because they are hidden, but because they are simply too far. In this way, the speed of light shapes not just what we can know, but what it means to be part of the universe. It defines the stage upon which the cosmic drama unfolds. It choreographs the timing of every star's light, every pulse from a quasar, every burst from a supernova. It tells us that we are not omniscient, that knowledge is earned, not given. And perhaps this is the greatest gift of all, because in placing a limit, the universe grants us the challenge of reaching. In establishing a speed, it gives us the thrill of pursuit. In defining the light cone, it draws the edge of the possible, and dares us to press against it, to lean into the unknown, to ask not just what lies within, but what it means to live at the boundary of light. Chapter 24. What light cannot touch. The horizon of the possible. Beyond the reach of even the swiftest photons, lies a realm we can never see, never touch, never know. It is not because it is hidden behind clouds or veils, but because it lies outside the very boundary of causality, the speed of light. In defining how far information can travel within a given amount of time, also defines the edge of the observable universe. And beyond that edge, beyond that shimmering cosmic boundary, lies a mystery as vast as it is unreachable. This is the cosmic horizon. It is not a physical wall, but a limit set by time itself. Because the universe has a finite age, and because light moves at a finite speed, there exists a maximum distance from which light could have reached us since the Big Bang. Anything farther away than that distance is, for now and possibly forever, beyond our ability to detect. It is part of the universe, but it does not participate in our story. This horizon is not fixed. It changes as the universe expands.
In a static cosmos, light would gradually illuminate more and more of the universe over time. But our universe is not static. It is not just expanding, it is accelerating. Galaxies are being pushed away from us faster and faster by dark energy, and the space between them is growing so rapidly that eventually their light will never reach us, even if it travels forever. Entire regions of the universe are slipping out of view, not because they are moving, but because the space between is expanding too quickly. This leads to a strange and haunting realization. The night sky is not a window into eternity, it is a window into a shrinking portion of the whole. Every year, more galaxies cross the event horizon of our observable universe, becoming unreachable. Their light, already stretched to near invisibility, will vanish entirely. What we see now is only a temporary glimpse, a passing alignment of time, distance and light. And yet, this limit gives our knowledge shape. It gives our maps of the cosmos definition. We can say with confidence how large the observable universe is. We can draw its structure, measure its age, and estimate its future. But every one of those statements carries a quiet disclaimer. We speak only of the visible, the knowable, the within reach. What lies beyond, whether more galaxies, other laws of physics, or nothing at all, remains outside the circle of light. This realization also brings a kind of humility. We are not the center of the universe, but we are the center of our observable sphere. Each point in space has its own horizon, its own set of reachable events, its own shrinking past and unreachable future. We do not see the universe as it is, we see it as it intersects with us. And every observer, in every galaxy, looks out upon a different boundary, defined by light, by time, by position. Still, the limit is not only spatial, it is temporal. The light we receive from distant galaxies was emitted billions of years ago. We are not seeing them as they are, but as they were. Some no longer exist, some have changed beyond recognition, and yet their light remains, a ghostly record of a moment long gone. In this way, the cosmic horizon is not just the edge of distance, but the edge of now. Beyond it lies not only other places, but other times. These limitations inspire not despair, but awe. For in constraining what we can know, the universe also defines what is worth knowing. We are bounded creatures, existing within a bounded world, but those bounds give structure to our question. They sharpen our tools, refine our theories, and focus our curiosity. And even as the edges of our view recede, we continue to press outward, seeking to understand not only what light can touch, but what it cannot. Quantum physics too respects this horizon. No quantum signal can exceed the speed of light. Entanglement may link particles across vast distances, but it does not allow information to travel instantaneously. The light cone remains intact. Cause still precedes effect. Even in the strangeness of the quantum world, the cosmic speed limit holds. Some theories suggest that our entire universe may be a patch of a much larger multiverse, with other regions beyond our light cone obeying different laws of physics. These ideas are speculative, untestable, yet they reflect our desire to extend the boundary, to reach beyond the horizon, to imagine a cosmos not limited by what light can show us. And though we may never see those places, the very act of imagining them is a form of exploration. We build telescopes that reach deeper, collect photons from farther back in time, stretch their arms toward the beginning of everything. We decode the messages in cosmic microwave background radiation, pass the signals from ancient quasars, extract meaning from the reddest galaxy, and in doing so, we expand the edges of our map, not by moving the horizon, but by pressing ever closer to its edge. In the end, the boundary defined by the speed of light is not a wall, it is a lens. It focuses our view, it sharpens our question. It reminds us that knowledge is always bounded by context, that understanding is a matter of perspective, and within that boundedness, within the fragile shell of what light can reach, lies a universe full of wonder, of richness, of depth. We may never touch what lies beyond the light, but in contemplating it we define who we are. We are beings who reach, who yearn, who imagine. The horizon is not our prison, it is our canvas. It is the edge of the known, and the invitation to dream beyond. Chapter 25. Light, Time and the Human Question. From the moment humanity first looked upward and wondered, light has been our guide, not just a physical beacon, but a symbolic thread pulling us toward understanding. We did not begin by knowing the speed of light, or even that light had a speed. We began with awe, with stories of gods and stars, with mythologies born from the patterns of the night. But over time, through centuries of patient curiosity, we arrived at a startling truth, that light moves, and that it moves not infinitely, but precisely, and that its movement defines what is possible in the universe. In the study of this one constant, we discovered the geometry of spacetime, the relativity of motion, the bounds of communication. We learned that light is not just fast, it is the fastest thing that can exist, and anything slower lives under its rule. Time itself, that most elusive quantity, flows differently depending on one's proximity to this limit. The closer we come to light speed, the slower our clocks tick, the shorter our journeys become. For the photon, there is no time, no waiting, no becoming, only instantaneity. But this revelation does not end in abstraction. It finds its deepest meaning in the human context, in how we live, how we perceive, how we dream. We are creatures of time. We age, we remember, we plan. Every heartbeat, every thought, every breath unfolds in time's current. And yet, the very tools we use to navigate this current, light, clocks, signals, stories, all obey a limit beyond which we cannot reach. What then does it mean to live in a universe where some things are forever out of sync, forever delayed, forever beyond? It means that we live in a reality of partial glimpses. We see the stars not as they are, but as they were. We send messages not instantly but at the mercy of distance. We watch supernovae from galaxies whose current state we may never know. Even our own sun is 8 minutes behind its true self, its image lagging just enough to remind us that we are always seeing the past. And yet, we build with this delay. We calculate it, correct for it, fold it into our equations and our lives. GPS satellites rely on relativistic timing. Internet signals bounce off orbiting mirrors at light speed. Telescopes are time machines. Fiber optic cables pulse with the heartbeat of civilization. The delay is not an obstacle, it is a law, and in following that law, we have created wonder. But we also encounter limits, ethical, philosophical, emotional. We ask, if the universe has a speed limit, does consciousness, can thought, tethered to neurons, ever touch the absolute? If information must crawl through the lattice of space-time, how can we ever truly connect across vast stretches? What does it mean to love someone on a star we'll never reach, to hope for a future we'll never see? These are not idle musings, they are the soul of science. Because science, at its best, does not simply reduce the world, it expands it. It takes the law, the limit, and finds freedom within it. The speed of light becomes not a fence, but a framework. It challenges us to find meaning in the delay, coherence in the separation, unity in the gap. And there is beauty in that challenge. For the same limit that keeps us apart also makes the universe stable. It prevents contradictions, paradoxes, instantaneous destructions of coherence. It preserves the flow of cause to effect, of event to memory. It ensures that history matters, that order exists, that stories can be told. And we are, perhaps more than anything else, storytellers. The photons we catch in our eyes become constellations, then myths, then coordinates, then equations, then images, then feeling. A galaxy seen today may be long gone, and yet, its light still dances in the lens of a telescope, still burns in the mind of a child, dreaming of space. That is not illusion, that is continuity, that is the miracle of limited light. So as we close this journey, a journey across chapters, across ideas, across the bounds of light and space and time, we return, not to finality, but to possibility, because the speed of light, though fixed, is not a barrier to imagination. It is the fuel of it. Gives shape to every dream of faster travel, every theory of connection, every vision of the stars. Without it, there would be no challenge, and thus no triumph. In every photon lies a question, in every delay a meaning,
In every journey a story, and in every mind that looks up and wonders, there lies the very same light, not of speed, but of understanding. The universe does not owe us simplicity, but it gives us structure, and within that structure, we find ourselves, bounded by time, moved by light, reaching always toward the horizon, not to break it, but to know it, and in knowing it, to become something more.